A beam of light racing from Earth takes over 4 years to reach even our closest stellar neighbor. At that speed, crossing our galaxy takes 100,000 years. We are trapped in a cosmic prison, locked behind bars made of physics itself. But what if those bars just bent? Scientists have cracked a method that could send spacecraft 10 times faster than light, turning century-long voyages into decade-long adventures. You'll discover warp bubbles appearing in laboratories, gravitational waves hiding alien footprints, and energy requirements dropping from impossible to just barely insane. Our fastest spacecraft ever built, the Parker Solar Probe, screams through space at 190,000 miles per hour. Sounds impressive, until you realize it would still take 70,000 years to reach the nearest star. That trip would begin during the last ice age and end in our distant future. Humanity is stuck in a speed trap we cannot escape with rockets alone. Light itself moves at 670 million miles per hour, and even that takes 4.5 years to bridge the gap between us and Proxima Centauri. The galaxy stretches 100,000 light-years across. Do the math, and crossing it becomes a journey spanning millennia. Every star you see twinkling in the night sky represents a destination that current technology renders completely unreachable within a human lifetime. The Voyager probes, launched in 1977, are now barely 14 billion miles from home. They've been traveling for nearly 5 decades. Yet they haven't even completely escaped our solar system's gravitational influence. The stars remain impossibly distant. We are cosmic infants crawling when we need to sprint. Here is the brutal truth. Space is not just big. It actively mocks our ambitions. The distances between stars are so vast that even traveling at 99% of light speed would turn interstellar missions into generational commitments. Your great-great-grandchildren might see the destination you aimed for. Every propulsion system we have built operates on the same basic principle. Throw stuff out the back to push forward. Chemical rockets burn fuel. Ion drives shoot electrified particles. Nuclear engines blast heated gas. All of them obey classical physics, and all of them crawl compared to the cosmic highway we need to cross. Scientists call this the tyranny of the rocket equation. The more fuel you carry, the heavier your ship becomes. The heavier your ship, the more fuel you need. It becomes a nightmare spiral, where your fuel tanks end up larger than entire cities just to reach a fraction of light speed. Adding more thrust only adds more weight. We have sent robots to Mars, landed rovers on distant moons, and photographed the edge of our observable universe. Yet we remain trapped in our own backyard, staring at fences we cannot climb. The nearest potentially habitable planet sits 4 light-years away. With current technology, getting there would require 25,000 years of continuous flight. Something has to change. The cosmos is filled with billions of potentially habitable worlds. Yet we can barely reach the closest rock in our own neighborhood. But what keeps us chained to this painfully slow reality? The answer lies in one man's equations, written over a century ago. Albert Einstein published his theory of special relativity in 1905, and with it, he built an invisible prison around humanity. His equations revealed something shocking. Nothing with mass can reach or exceed the speed of light, ever. The universe itself enforces this rule through the fabric of space and time. The reason sounds deceptively simple. As objects accelerate closer to light speed, they gain mass, not just a little bit. The faster you go, the heavier you become. Not gradually, exponentially. A spacecraft approaching light speed would weigh more than entire galaxies, move at 1 more mile per hour faster, and the energy requirement jumps so dramatically that it becomes absurd. Astronomical doesn't even begin to describe it. This creates a cosmic trap. You need energy to accelerate mass, but accelerating makes that mass increase, which requires more energy, which increases the mass further. The cycle spirals upward, faster and faster, until it hits a wall at light speed itself. The universe essentially says, you can get close, but you can never cross this line. Einstein called it a universal speed limit, and for over 100 years, his math has held. Particle accelerators smash atoms together at 99.99% light speed, and they confirm his predictions with terrifying precision. Objects really do get heavier. Time really does slow down. The rules are absolute. Scientists have tried everything to find a loophole. Exotic propulsion methods, gravitational assists, generation ships where entire civilizations would be born, live and die during the journey. None of it works. Einstein's equations lock the door. Conventional physics cannot find the key. Physicists call these laws inviolable. Break them, and you break causality itself. Effects happen before causes. Paradoxes cascade. The logical structure that holds reality together tears apart. The universe would rather collapse than let something with mass exceed light speed. And it gets worse. Time dilation warps your experience. Reach 99% of light speed, and time flows differently for you than for everyone back home. A journey that feels like 10 years to you might span decades or centuries on Earth. You would return to find everyone you knew long dead, their great-grandchildren now elderly. The isolation is absolute. Then add length contraction. Space itself compresses in front of you. Distances shrink. A trip that should take years might feel like months to you, while decades pass outside. The universe warps around fast-moving objects in ways that defy intuition. For generations, physicists accepted this. Light speed is the limit. Nothing escapes it. Teaching this became fundamental to every physics classroom on Earth. Breaking it seemed as impossible as making a square circle or forcing 2 + 2 to equal 5. But then some scientists refused to surrender. They asked a different question. What if we're thinking about movement all wrong? Because here's the brutal reality. Accelerating even a small spacecraft to light speed requires more energy than currently exists in every fuel tank, battery, and power plant on Earth combined. Then multiply that by 1 billion. You still fall short. The mathematics are ironclad. As velocity increases, so does kinetic energy. Near light speed, energy requirements don't just grow, they explode. A spacecraft weighing just 1 ton needs approximately 9 × 10⁻16 joules to reach light speed. That's the total annual energy output of human civilization consumed in seconds, just to move one small vehicle. Nuclear fusion, the same process powering stars, offers our most energy-dense fuel. Yet converting the entire mass of a large asteroid into pure energy would barely nudge a decent-sized starship to a meaningful fraction of light speed. We're not talking about difficult engineering problems anymore. We're talking about fundamental impossibilities. Project Daedalus, designed in the 1970s, proposed using fusion rockets to reach 12% of light speed. 12% sounds modest until you see the design. A ship mostly composed of fuel tanks the size of skyscrapers, carrying 50,000 tons of deuterium and helium-3, just to push a probe to a fraction of our cosmic speed limit. Reaching for the stars. Imagine a ship so enormous that the cargo hold, the entire compartment, meant to carry actual people and supplies, is barely visible inside it, dwarfed, insignificant. And even with all that mass, all that engineering, it would still take 20 years just to reach the edge of our nearest star system. We're talking about our closest cosmic neighbor, and it takes 2 decades to get there. Now, physicists have dreamed up something better: antimatter. When matter and antimatter collide, they don't just react, they obliterate each other completely. And in that annihilation, 100% of their mass transforms directly into pure energy. It's the holy grail of fuel, the most efficient power source theoretically possible. There's a catch. We can only make antimatter one particle at a time, using colossal particle accelerators that are already some of humanity's most expensive machines. And storing it? That requires magnetic bottles consuming tremendous amounts of power just to keep the antimatter from touching the walls and destroying everything. To gather enough antimatter for a single interstellar mission, using our current technology would take thousands of years. Thousands. That's not an exaggeration. That's the math. Other researchers have proposed something radically different: solar sails. Imagine enormous, reflective sheets, miles across, thin as gossamer, pushed through space by nothing but light pressure from distant stars. No engines, no fuel, just the gentle pressure of photons doing the work. The problem? The acceleration is agonizingly slow. We're talking fractions of inches per second. Glacial doesn't even begin to describe it. To reach just 10% of light speed would demand decades of continuous acceleration. And that sail would need to be impossibly thin, impossibly large, yet somehow strong enough to hold itself together without tearing apart from the strain. But here's what really matters. Every single method we've tried, chemical rockets, ion drives, nuclear engines, fusion reactors, they all hit the same barrier. The faster you want to go, the more fuel you need. The more fuel you carry, the heavier your ship becomes. The heavier your ship, the more energy you need to accelerate it. Engineers call this diminishing returns. Physicists call it the wall. Chemical rockets reach about 5 miles per second. Ion drives might manage 20 or 30. The best nuclear thermal engines could theoretically hit 50 miles per second. Even the most optimistic fusion designs, the ones that don't exist yet, remember, max out around 3,000 miles per second. That sounds impressive until you realize it's only 1% of light speed. We are throwing pebbles at a mountain and hoping to move it. But the real trap isn't about building bigger engines or finding better fuel. It's something deeper. It's written into reality itself. Einstein showed us the truth. Reaching light speed requires infinite energy. Infinite. Not a lot. Not an unfathomably large amount. Infinite. And infinity is impossible. No breakthrough technology changes that. No clever engineering gets around it. No amount of human determination rewrites those equations. Unless. What if movement itself isn't what we think it is? Because here's the thing that keeps scientists awake at night. Earth is dying, and we have nowhere else to go. Our solar system is a graveyard of hostile worlds. Start with Mars. It's the closest option, the one we talk about colonizing. But Mars is a frozen nightmare. Temperatures plummet to minus 225 degrees Fahrenheit. The atmosphere is 96% carbon dioxide, and so thin that standing on the Martian surface would be like standing 19 miles above Earth. Your blood would literally boil in that low pressure. Dust storms rage across the entire planet for months at a time, and radiation from space hammers the surface constantly because Mars lost its protective magnetic field billions of years ago. Venus? Even worse. Beneath those thick clouds, the surface temperature reaches 860 degrees Fahrenheit, hot enough to melt lead. The atmospheric pressure equals what you'd experience 3,000 feet underwater on Earth. The air itself is mostly carbon dioxide mixed with clouds of sulfuric acid. Every probe we've sent to Venus has survived less than 2 hours before being crushed and melted. The gas giants offer no surface at all. Jupiter, Saturn, Uranus, Neptune, they're just enormous balls of hydrogen and helium, with crushing pressures and winds exceeding 1,000 miles per hour. Their moons are slightly better, technically, but they're frozen, airless, and lethal. Titan, Saturn's largest moon, is the closest thing to habitable in the outer solar system. It has liquid methane lakes and a thick atmosphere, and yet it's still a world where the temperature drops to minus 290 degrees Fahrenheit, where any exposed human would freeze solid in seconds. We are trapped in a cosmic prison. The walls are physics. The bars are distance. Imagine a world where the thermometer doesn't just dip below freezing. It plummets to minus 290 degrees Fahrenheit. You wouldn't shiver. You wouldn't even scream. You'd freeze solid in seconds. Welcome to Europa, Jupiter's moon, which hides something extraordinary beneath miles of ice: liquid water. But here's the catch. To reach it, you'd have to drill through a frozen shell while being bombarded by radiation so intense it would cook you alive. Then there's Mercury, swinging wildly between 800 degrees on its sun-facing side and minus 300 degrees in shadow. The moon? No atmosphere, no water, no magnetic shield to deflect the cosmic assault that Earth's protective bubble keeps at bay. Every single world in our solar system is hostile, too hot, too cold, too toxic, or simply missing the basics you need to survive. Mars seems like the closest thing to a backup plan, until you do the math. To make it barely livable would take thousands of years. We'd need to thicken its atmosphere, warm its surface, resurrect a dead magnetic field, create breathable air from scratch. Each challenge is nearly impossible. Each one demands technology we haven't even invented yet. But here's the brutal truth. Earth isn't just our home. It's our only home for potentially millions of years. If climate change strikes, if an asteroid impacts, if any catastrophe renders this planet uninhabitable, humanity has no escape hatch, no backup, no plan B. We need to reach beyond our solar system, not for adventure, for survival. The problem: the worlds that could save us might as well be in another universe. 4 light years away, Proxima Centauri b orbits in its star's habitable zone, that perfect distance where liquid water exists on the surface. 39 light years distant, the TRAPPIST-1 system hosts 7 Earth-sized planets, 3 of them potentially habitable. 1,400 light years away, Kepler 452b, Earth's cousin, mirrors our own planet so closely, it feels like looking in a mirror across an uncrossable gulf. We can see these worlds. Our telescopes have cataloged over 5,000 confirmed exoplanets. We measure their sizes, analyze their composition, calculate their surface temperatures. We know which ones could have atmospheres, which ones might have oceans, which ones could harbor life. We can see everything about them. We just can't get there. This is why faster-than-light travel isn't some luxury dream for interstellar tourism. It's an evolutionary imperative. It's the difference between humanity's long-term survival and extinction. Because the speed of light isn't just a cosmic speed limit. It's a prison wall. And we need to break through it. Proxima Centauri b haunts astronomers precisely because it represents everything we want and everything we cannot have. Just 4.2 light-years away, it orbits a red dwarf star in the habitable zone. It might have oceans. It could harbor life. Early data suggests it possesses a magnetic field, a shield against radiation that could protect any life there. Energy levels matching what Earth receives from our sun. It's perfect. It's impossibly close, and it's untouchable. Then came 2017, the TRAPPIST-1 system. 7 Earth-sized planets orbiting a small, cool star, just 39 light-years away. Not 5, not 3, 7. 3 of them sit squarely in the habitable zone. Computer models don't just suggest they could have atmospheres. They predict weather systems, stable climates, the whole package. Liquid water isn't just possible, it's likely. Scientists detected hints of atmospheric composition. The excitement was palpable. We'd found not just one candidate, but a system. Then Kepler 452b arrived. Nicknamed Earth's cousin, this world orbits a star so similar to our own it feels like cosmic symmetry. It receives only 10% more solar energy than Earth does, which means surface temperatures in exactly the right range for life. It's 1/400 light-years away, and discovering it felt like finding a twin sibling separated from you by an ocean you can never cross. And these discoveries keep multiplying. Every year brings dozens of new candidates, worlds with thick atmospheres, planets with day-night cycles just like ours, rocky worlds with precisely the right mass to hold on to their air without crushing everything on the surface, frozen worlds, lava worlds, ocean worlds, desert worlds. We've found dozens, then hundreds, then thousands. The universe, it seems, is littered with possibilities, and we're stuck here, staring at them through a telescope, unable to move. We stand at the edge of an cosmic ocean, gazing at islands of possibility that shimmer just beyond reach. Proxima Centauri b, our closest neighbor in this infinite darkness, would take 40,000 years to reach with our fastest spacecraft. Not centuries, not millennia. 40,000 years. That's longer than human civilization has existed. TRAPPIST-1, 600,000 years of continuous flight. Kepler 452b, 25 million years. These aren't travel times anymore. They're geological epochs. They're the time it takes continents to drift, mountains to erode, entire species to evolve and vanish. We have become spectators in our own cosmic neighborhood. The James Webb Space Telescope peers across dozens of light years and reads the chemical fingerprints of distant atmospheres. It detects water vapor. It finds oxygen. It shows us worlds that might harbor life, might sustain civilizations, might be havens if Earth ever becomes inhospitable. And yet, we cannot reach them. We cannot even send a small probe in any reasonable time frame. It's like being a prisoner behind glass, watching banquets you will never taste, cities you will never enter. The cruelty cuts deeper than mere frustration. These planets could be humanity's future homes. They could overflow with ecosystems to study, resources to harvest, perhaps even civilizations waiting to meet us. Everything we desperately need to know, everything we might desperately need to survive, it all sits just beyond an insurmountable wall of distance and physics. A radio signal traveling at light speed would take years just to arrive. If we detected alien intelligence today and sent a message, their reply wouldn't come back until decades had passed. A simple conversation would span generations, playing out across human lifetimes like a chess game between immortals. Traditional space travel is a dead end. We need something radical, something that doesn't just push harder against the cosmic speed limit, but breaks it entirely. Enter Miguel Alcubierre, a graduate student obsessed with Star Trek. In 1994, he asked a question that might sound insane. What if warp drive actually worked? Not as science fiction, as real physics. He did the math. His equations were technically flawless. Professional physicists read his paper and stopped what they were doing because Alcubierre had discovered something extraordinary hidden inside Einstein's own theories. a loophole so elegant, so obvious in hindsight, that nobody had fully exploited it before. Here's the genius. Einstein's equations say nothing with mass can move through space faster than light, but they never say space itself cannot move faster than light. In fact, we know space breaks this rule constantly. At the very edge of the observable universe, space expands faster than light. This expansion is how the universe grew from an infinitesimal point to its current incomprehensible size in just under 14 billion years. So if space already violates the speed limit, why not harness that power? Alcubierre's insight was radical and beautiful. Don't accelerate the spacecraft through space. Warp space around the spacecraft instead. Picture a surfer on an ocean wave. The surfer isn't swimming, isn't creating their own speed. They're standing still on their board while the ocean carries them forward. The wave does all the work. Alcubierre's drive operates identically. You create a bubble of warped spacetime around your ship. Space contracts violently in front of the vessel, crushing inward like a fist. Behind the ship, space expands, pushing outward. The bubble itself gets carried forward by this asymmetric distortion. The spacecraft inside remains perfectly still, relative to the space immediately around it. No acceleration forces, no G-forces crushing the crew, no thrust engines roaring. The ship simply surfs the geometry of space-time itself, and the math works. The equations are sound, published in peer-reviewed journals. Legitimate theoretical physics. Not speculation, not hand-waving. Real mathematics from general relativity, proving that faster-than-light travel isn't forbidden by the laws of physics, only by the practical engineering challenges of actually building it. For the first time in human history, someone had mathematically proven that the stars might not be forever out of reach. There's a problem with the laws of physics, or rather, there isn't one. A young physicist sat down with his equations, inspired by his favorite TV show, and did something remarkable. He found a loophole, not a glitch in the system, a genuine feature hidden in the structure of reality itself. When other scientists checked his work, they couldn't find an error. The math held. According to everything we know about relativity, it should work. Space-time could be warped without breaking causality, without violating Einstein's laws. The energy cost? Astronomical. Genuinely staggering. But, and this matters, finite. Actually finite. Not infinite. Let me put that in perspective. Conventional propulsion requires literally infinite energy just to touch light speed. The universe makes it impossible. But this method? This method requires only extraordinary amounts of energy. That's not just an improvement, that's a revolution hiding inside the equations. His name was Miguel Alcubierre, and he may have discovered a cheat code buried in reality's operating system. Here's the insight that makes it work. Space-time is not empty. It's not nothing. It's an actual thing, a fabric. And fabrics can bend. Every massive object creates a dent in that fabric, like a bowling ball sitting on a rubber sheet. That dent is gravity. Einstein figured this out over a century ago. We've confirmed it countless times. GPS satellites have to account for it. Atomic clocks on airplanes measure it. Black holes prove it so violently that nothing, not even light, can escape. The Alcubierre drive takes this principle and weaponizes it. Instead of letting gravity naturally curve space around you, imagine artificially creating a bubble of warped space-time. Inside that bubble, you place your ship. Then you contract space in front of you, squeeze it down, while expanding space behind you. This creates a wave. The wave pushes the bubble forward. Your ship never moves through space. Space moves around your ship. It sounds like semantics until you realize what this actually means. You've just sidestepped Einstein's speed limit entirely. Relativity restricts how fast you can move through space. It doesn't restrict how fast space itself can move. That distinction is everything, because here's what happens when you're not actually moving through space. Time doesn't slow down. Your body doesn't stretch and compress. You don't age slower than people back home. You don't see distances melt away into cosmic blur. Inside the warp bubble, physics is completely normal. You can walk around, drink coffee, play cards, experience time flowing at exactly the same rate as people on Earth. No twin paradox, no relativistic nightmares. The bubble isolates you from the violent distortions happening at its edges, while the wave itself can travel at any speed. 10 times light speed? Relatively straightforward, according to Alcubierre's calculations. 100 times? More recent variations suggest it's possible. 1,000 times? Theoretically, yes. At those velocities, Proxima Centauri, our nearest star, becomes a 2-week journey. The entire Milky Way becomes crossable in a human lifetime. A lifetime. Not thousands of years. Not millions. One life. The universe would see something strange approaching. The compressed space in front of the bubble would trap light. To distant observers, your ship would be partially invisible, cloaked by crushed spacetime. Behind you, the expanding space would shift light to radio wavelengths, creating a fading ghost of your passage. But inside, everything is normal. Everything is possible. Alcubierre himself never expected his recreational calculation would work. He was just a physics student playing with equations, inspired by television. He was not trying to rewrite physics. He was not trying to unlock the universe. He was just writing math for fun. And he accidentally found the door. The impossible suddenly looked merely extremely difficult. Imagine you're traveling through space at the speed of light, wrapped inside a bubble of normal reality. Around you, space-time itself is rippling like an ocean wave. The universe bends and compresses ahead of you, pulling distant stars close enough to touch. Behind you, space stretches away into an infinite ribbon, though you can still see where you came from, just painted in colors you've never seen before. The light from distant galaxies shifts and warps as it passes through the space-time bubble surrounding you. You're surfing on reality itself, letting the universe do all the work while you sit comfortably, untouched by the violent geometry writhing outside your protective shell. This is the dream at the heart of the Alcubierre warp drive, and it's almost elegant in its simplicity. The trick? Create asymmetric space-time curvature. Manipulate the energy density of space itself. Make reality bend in ways that seem almost like magic. The mathematics gets complex fast. Tensor equations, differential geometry, the full arsenal of Einstein's toolkit. But the concept is pure poetry. Bend space, not yourself. And then reality crashes down. Because Alcubierre's warp drive requires something we've never found. Something we've never created. Something we're not even sure exists. Exotic matter. Not antimatter. That's the stuff that annihilates when it touches normal matter, in brilliant, catastrophic explosions. No, exotic matter is stranger than that. It's the opposite of everything we know about mass and energy. Normal matter attracts. It curves space-time inward, creating gravitational wells that hold planets in orbit and make apples fall from trees. Exotic matter? It repels. It pushes instead of pulls. It curves space-time outward, like a gravitational hill trying to shove everything away. It would have negative mass, negative energy density. Imagine something that gravity runs backward for. Imagine something that repels instead of attracts. We've never observed it, never measured it, never created it in a laboratory, or found it anywhere in the cosmos. It exists only in the equations of general relativity, a mathematical possibility that the universe apparently decided not to actually build. But here's where it gets worse. The amount of exotic matter needed for a warp drive isn't a teaspoon or a ton. Alcubierre's calculations showed you'd need negative mass equivalent to the entire mass energy of Jupiter, just to warp space around a small spacecraft. Jupiter, 300 times heavier than Earth. Even if you somehow manage to convert normal matter into this exotic stuff, which we have no idea how to do, the energy required would be staggering. We're talking about power expenditures that make humanity's entire energy output look like a candle in a hurricane. Scientists immediately saw the problem. The math works, they admitted. The equations are perfectly valid. The physics checks out. But demanding materials that don't exist? That's like designing a perpetual motion machine that runs on unicorn tears. Beautiful in theory, impossible in practice. So researchers got creative. Could electromagnetic fields somehow create negative energy density in vacuum? Could we manipulate quantum fluctuations? Dark energy, that mysterious force pushing the universe apart, seems to have properties similar to negative pressure. Could we harness that? Decades of theoretical papers followed. Brilliant minds chased brilliant ideas, and they all hit the same wall. The universe appears to have built-in protections against creating large regions of negative energy density. It's as if reality has a defense system. The deeper you dig into quantum field theory, into the energy conditions that govern how the cosmos works, the more you realize the universe doesn't want you making regions of negative energy. Allowing that could break causality. It could unleash paradoxes. It could tear holes in reality itself. But then a tiny glimmer of hope appeared. The Casimir effect. Place two uncharged metal plates extremely close together in a vacuum, closer than the wavelength of light. Quantum fluctuations in the space between them create slightly less energy density than in the surrounding space. Technically, that's negative relative energy density. It's tiny. The absolute energy values are still positive. The effect is minuscule, almost unmeasurable, but it's real. It's confirmed, and it actually works. For the first time, we had proof that the universe could produce something that behaved like negative energy, even if only in the smallest, most fragile form. A single glimmer in the darkness. A crack in the door that the universe had supposedly locked shut. Here's the question that changes everything. What if you didn't need exotic matter at all? What if you could bend spacetime using only physics we already understand? The Casimir effect, that strange quantum dance between metal plates where virtual particles create measurable forces, might be the key. Scale it up, manipulate it, create the exact distortions an Alcubierre drive demands, but without chasing theoretical ghosts that may never exist. The energy problem remains. You'd still need power from somewhere, but at least you'd be working with the real, the testable, the known. This is where Harold White enters the story, and where everything changes. White spent years at NASA's Johnson Space Center in Houston studying propulsion physics, the kind of fringe science that makes colleagues roll their eyes but occasionally produces breakthroughs. In 2011, he published calculations that shattered decades of assumptions. The energy requirements for an Alcubierre drive, he showed, might be dramatically lower than anyone thought. By optimizing the bubble's shape, you could slash the power needs by several orders of magnitude. Not Jupiter's mass in exotic matter anymore, just several hundred kilograms. Still impossible to obtain? Yes. Still unavailable? Absolutely. But the equation had fundamentally shifted from physically impossible to merely incredibly difficult. Then 2021 arrived. White's team was running routine experiments with the Casimir effect, using specialized equipment to measure nanoscale forces between metal plates. They weren't trying to build a warp bubble. They were just investigating whether Casimir forces could help with spacecraft attitude control. Basic research. Nothing revolutionary. Except during one experimental run, their sensors detected something that shouldn't exist. A measurable warp in spacetime at the nanometer scale. The readings matched the theoretical predictions perfectly. They had accidentally created the exact spacetime geometry that Alcubierre described, just millions of times smaller than needed for actual propulsion. They repeated it, again and again. The effect held. Consistent, measurable, not instrument noise, not quantum static. Actual, repeatable, space-time distortion created by manipulating the Casimir effect. A warp bubble, microscopic but absolutely real, had appeared in a laboratory on Earth. The implications detonated through the propulsion physics community. Warp drive geometry wasn't theoretical anymore. It was measurable. It was repeatable. It existed. If you could create a nanoscale warp bubble in a lab, then scaling it up became an engineering challenge rather than a fundamental physics impossibility. Skepticism emerged immediately. Other labs needed to reproduce the results. The equipment is specialized. It's expensive. Independent verification takes time. Some physicists offered alternative explanations. Electromagnetic interference, misinterpreted quantum effects. That skepticism is healthy. Science demands it. But White's team had calibrated their instruments with precision. They accounted for known sources of error. They documented everything meticulously. The data looked solid. More importantly, the effect appeared exactly when theory predicted it should appear, and vanished when conditions changed. That correlation between prediction and observation is the fingerprint of real phenomena, not measurement artifacts. NASA quietly increased funding for White's lab. Other government agencies took notice. Private aerospace companies began hiring propulsion physicists to investigate warp field generation. The race was on, not to build a working warp drive tomorrow, but to answer the question that could reshape human spaceflight. Could you scale a nanoscale warp bubble up? Could you turn this laboratory curiosity into an engineering problem we might actually solve? The answer was no longer obviously no. There's a problem that won't go away. Even if we crack the energy budget, we still need something physics barely tolerates: negative energy density. We need to bend spacetime in ways the universe actively resists. Then Harold White did something remarkable. His experiments showed that the Casimir effect, a phenomenon lurking at the quantum scale, could produce warp-like geometry. Real, measurable distortions in spacetime. The catch? It only worked at scales measured in nanometers, with energy manipulation so tiny it barely registered. Scaling that up to something useful means jumping 1 billion times larger. A billion-fold leap from the infinitesimal to the real world. But something crucial had shifted. Warp bubbles weren't just mathematical fantasies anymore. They existed in laboratories, in actual experiments, under actual instruments. That realization shattered something psychological. Suddenly, every physicist who'd filed away warp drive papers decades ago started pulling them back out. Maybe the answer wasn't hidden in some exotic new physics. Maybe it was hiding in plain sight all along, and it was. It was hiding in the weirdest, most unsettling truth About reality itself. Empty space is not empty. Quantum field theory tells us something almost absurd. The vacuum, that perfect, infinite nothingness between the stars, is actually churning, constantly. Particles are blinking into existence and vanishing again, faster than the universe can catch its breath. Virtual particles. They borrow energy from quantum uncertainty itself, exist for infinitesimal fractions of a second, then wink out before reality even notices the debt. You can't see them directly. They're ghosts made of mathematics, but they leave fingerprints. Their effects are real, measurable, undeniable. They create a faint background energy that saturates all of space, what physicists call quantum vacuum energy. Normally, this energy presses equally in every direction, so it cancels out. You never notice it. The universe feels perfectly normal. Then in 1948, a Dutch physicist named Hendrik Casimir made a prediction that shouldn't have worked, but did. What if you took two completely uncharged metal plates, no charge, no magnetic field, nothing, and pressed them incredibly close together? Closer than a human hair is thick. Something strange should happen. The metal plates act like a cage. They restrict which virtual particles can exist in the gap between them. Only particles with wavelengths smaller than the gap can squeeze in. Outside those plates, all wavelengths of virtual particles exist freely, without restriction. This creates an imbalance. More quantum pressure, pushing the plates together from the outside than pushing them apart from the inside. The plates should attract each other. They should move toward each other. And they do. They attract with measurable force, despite having no charge, despite having no conventional interaction whatsoever. They are being pushed together by an imbalance in the quantum vacuum itself. The force is tiny, only noticeable when the gap shrinks below a micrometer, but it is absolutely real. Scientists have measured it hundreds of times. The Casimir effect proves something extraordinary. Negative energy density can exist in nature. The space between those plates has less quantum vacuum energy than normal empty space. It's negative energy relative to the surrounding vacuum. This changes everything, because if Casimir effects could produce negative energy in small quantities, maybe, just maybe, exotic matter wouldn't be necessary for warp drives at all. White understood this. His team didn't just measure the Casimir effect, they weaponized it. By arranging capacitor plates in specific geometric patterns, they created regions where quantum vacuum energy deviated from baseline. Energy density differences, distortions in spacetime itself. The warping was microscopic, almost infinitesimal, but it was there. It was real. Now comes the problem, scaling it up. The Casimir force doesn't cooperate. Move those plates even slightly farther apart, and the effect collapses. Gone. Creating negative energy densities across meter-scale distances instead of nanometer scales requires technology that doesn't exist yet. Some physicists proposed metamaterials, artificially engineered structures that bend light and electromagnetic fields in impossible ways. Others imagined quantum computers precise enough to control vacuum fluctuations directly. A few radical minds even wondered, could dark energy, that mysterious force tearing the universe apart, be related to manipulable vacuum states? Could we weaponize the cosmos itself? But there's a deeper problem. Even if we solve the scaling, even if we harness the quantum vacuum, the energy requirements are still staggering. You don't just create a warp bubble once and forget about it. You have to maintain it. You have to hold those sharp energy gradients stable against the pressure of spacetime itself. That demands power sources beyond anything human civilization has ever built. We're not talking about solar panels or fusion reactors. We're talking about capturing the fundamental energy of reality itself. The universe is telling us, you're getting close, but not quite close enough. Not yet. Nuclear fusion, warp drives, and the art of bending space. Nuclear fusion could give us the power, concentrated, raw, almost unlimited power. But raw power isn't enough. You need control. You need precision. You need to bend the fabric of reality itself, and do it exactly. That's a different beast entirely. But here's what changed everything. The door cracked open. And what came through wasn't what anyone expected. For decades, physicists assumed you'd need exotic matter, this bizarre, hypothetical substance with negative energy density. It seemed essential, a requirement written into the laws of physics themselves. But what if they were wrong? What if ordinary physics, the stuff we can actually measure and touch, could do the job? That wasn't just a small adjustment. That was genuine progress. Not speculation, not hope. Progress. The next chapter would come from an unexpected place. Listening. Listening to the universe itself, searching for signals that maybe, just maybe, someone else had already figured this out. When Miguel Alcubierre first ran the numbers on his warp drive concept, he got numbers that made physicists go quiet. To warp space the way his equations described, you'd need to convert Jupiter, the entire planet, into pure energy. Every atom, every molecule, all of it. The math spat out a number, roughly 2 × 10 to the 47th joules. Put that in perspective, the most powerful nuclear weapon humanity ever detonated, the Tsar Bomba, released about 2 × 10 to the 17th joules. You would need that bomb's entire explosive yield, multiplied by a trillion times. A trillion. That's not exaggeration. That's literally what the math demanded. The physics was elegant. Relativity allowed it, but reality was brutal. You'd need the energy output of multiple star cores. The entire concept crashed to the ground. A theoretical curiosity. A ladder to the moon. Interesting to think about. Impossible to build. Then Harold White looked at those equations more carefully, and he noticed something everyone else had missed. The energy requirement wasn't fixed. It depended on 2 things: how thick you made the warp bubble's walls, and what shape you gave the bubble itself. Alcubierre had used relatively thick walls in a simple sphere. He chose that design because it made the mathematics cleaner, easier to solve by hand. But what if you didn't have to use that design? What if you optimized? White had an idea. Instead of a sphere, reshape it into a torus, a donut. Then, and this was the crucial part, don't keep the walls uniform. Make them oscillate. Make them pulse. Vary their thickness dynamically. The math became ferociously complex, but computers didn't care about complexity. They chewed through it. When White ran the optimized numbers, people in the room literally stopped talking. The energy requirement didn't just drop, it collapsed. From Jupiter mass to something closer to 500 kilograms of exotic matter equivalent. Still enormous, still exotic, but orders of magnitude, multiple orders of magnitude, more reasonable. 500 kilograms. That's about the weight of a small satellite. You could fit it inside a spacecraft. You wouldn't need a star, and that wasn't the end. Other research groups started working through different geometries. Elongated ellipsoids, figure 8 configurations, nested shells with varying densities. Each one trimmed the energy requirement further, like watching engineers refine rocket nozzles over decades. Same physics, smarter design. Recent papers propose something almost unthinkable. You might only need dozens of kilograms of negative energy density. If you get the geometry exactly right, dozens. This wasn't a breakthrough in fundamental physics. This was optimization. It was humans doing what humans do best, taking an impossible problem and chipping away at it with cleverness and mathematics until it becomes merely implausible. But then came the real game changer. Researchers started asking, do you actually need the exotic matter permanently? What if you could create temporary bubbles? Ordinary energy channels through quantum effects, generating tiny regions of negative energy density that exist for just long enough to produce thrust. Then they collapse. Then you create new ones, pulse after pulse. You wouldn't be storing a 500-kilogram exotic matter engine. You'd be generating space-time distortions on demand, using ordinary energy borrowed from the quantum foam itself. That changed everything, because that meant the impossible might not be impossible after all. Imagine an engine that doesn't burn fuel smoothly and continuously. Instead, it fires in pulses, explosive bursts of controlled energy, one after another. Now imagine that same principle applied to bending spacetime itself. This pulsed warp drive concept could run on something we actually understand: advanced fusion reactors, or even antimatter annihilation. No need to store exotic matter. No need to keep it stable indefinitely. You'd need exotic spacetime effects, yes, but only in brief, controlled moments. That changes everything. Suddenly, the challenge isn't finding miracle materials that don't exist. It's a precision engineering problem. It's difficult, but it's the kind of difficult humans have solved before. Does it actually work? The math checks out. Multiple independent physicists have verified it. The equations are sound. But here's the brutal truth. Mathematics only describes what might be possible within the laws of physics as we understand them. Reality doesn't always cooperate with our equations. Not until someone actually builds it. Yet something profound has shifted. The energy requirement has plummeted from the mass of Jupiter to the mass of a satellite. That's not just a number on a page. That's the difference between impossible and merely extraordinarily difficult. And sometimes that distinction changes everything. But other physicists weren't satisfied with incremental improvements. Brazilian physicist José Notario looked at the original warp drive equations and saw something Alcubierre had missed. In 2002, he published a completely different solution. The Notario drive uses different geometric tricks to bend spacetime, and some physicists argue it's fundamentally more stable. Here's the key difference. Alcubierre's design creates sharp, violent boundaries at the edge of the warp bubble. Space suddenly compresses, then expands. It's like a cliff edge. Those sharp transitions demand enormous energy concentrations in tiny regions. They might generate dangerous radiation. They might create gravitational instabilities. Notario smoothed them out. Instead of brutal discontinuities, his model spreads the spacetime distortion gradually across a much larger volume. Energy densities drop everywhere because the load is distributed. Think of it like the difference between a cliff and a slope. Both change elevation, but a slope is inherently more stable. You don't need extreme engineering to traverse it. This seemingly small change has profound implications. Alcubierre's sharp boundaries might be vulnerable to quantum instabilities, the kind of microscopic fluctuations that could cause the entire bubble to collapse. Notario's gentler transitions might naturally stabilize themselves. The design also appears to reduce problematic side effects at the bubble edge, like Hawking radiation. That eerie phenomenon where quantum effects at extreme boundaries create particles and energy. The energy costs remain roughly comparable to optimized Alcubierre drives, but the engineering demands shift. Instead of creating extreme concentrations of warping at a single point, you need to create milder, but more spatially extended distortions of spacetime. Counterintuitively, that might actually be easier. Casimir effects, or electromagnetic field manipulation, might achieve this without demanding the impossible. There's a catch, though. The mathematics becomes even more complex. You're manipulating advanced tensor fields. You need cutting-edge differential geometry, just to describe it properly. Most popular explanations stick with Alcubierre's model because it's simpler to visualize. People can wrap their heads around it. The Natario drive? That takes serious mathematical sophistication. Some researchers now propose something radical, a hybrid. Combine Natario's stable, smooth boundary geometry with Alcubierre's oscillating, energy-efficient bubble walls. Merge the best features of both designs. In theory, you'd get stability and efficiency. Meanwhile, at the University of Göttingen in Germany, another team asked a different question entirely. What if the shape of spacetime itself, its fundamental topology, could be optimized in ways nobody had considered yet? Imagine treating spacetime itself like clay. You could sculpt it into bubbles. You could twist it into toroids. Or you could braid it, weave it, fold it into helical spirals. Geometries so creative, they seem pulled from impossible mathematics. And here's the stunning part. The math actually works. These aren't fantasy. They're real solutions to Einstein's equations, sitting there waiting to be explored. We've gone from one wild idea, warp drives are theoretically possible, to multiple competing visions of how they might actually work. That's the sign of something real taking shape. Different designs might excel at different missions. Short jumps could use one configuration, interstellar voyages another. Just as we build fighter jets differently than cargo planes, warp drives might come in countless varieties, optimized for countless purposes. But here's what hasn't happened yet. We've never built even a centimeter-scale prototype. We haven't tested whether the mathematics transforms into physical reality. Not a single warp drive exists. Which raises an urgent question that researchers began asking. What if we're not the first? What if somewhere out there in the cosmos, an advanced civilization already cracked this problem centuries ago, millennia ago? And if they did, could we detect them? Here's where it gets interesting. Gravitational waves ripple through spacetime whenever massive objects accelerate violently. Colliding black holes, merging neutron stars, supernovae detonating across the galaxy. They all broadcast waves that travel at light speed, and we can measure them now. LIGO and Virgo are so sensitive, they can detect space-time distortions smaller than a proton. In 2024, researchers at Germany's University of Potsdam asked a brilliant question. If warp drives bend space-time, wouldn't they also create gravitational waves? The answer is yes. And more than that, those waves would have a signature, a fingerprint, a pattern completely different from anything nature produces on its own. They ran the simulations. They calculated the frequencies, the amplitudes, the polarization patterns. They knew exactly what an alien warp drive would look like to our detectors. Then they searched through existing gravitational wave data. Nothing. But here's the catch. We've only been listening to the universe this way since 2015. We're infants in gravitational wave astronomy. The detectors coming online in the next decade will be thousands of times more sensitive. They'll hear signals we can't even imagine right now. Consider what this means. If any advanced civilization within a few billion light years has developed warp drives, we could detect them, not by building warp drives ourselves, not by traveling to their home worlds, but by seeing the gravitational ripples their ships leave behind. expanding shells of distorted spacetime, washing across the galaxy at light speed, eventually reaching Earth. Each detection would be a Rosetta Stone. We'd learn how they engineered it, the energy signatures, the bubble geometries, the propulsion methods. Finding one warp drive signature would prove the concept works. It would be like discovering alien footprints and reverse engineering their shoes from the imprint alone. Now, skeptics will say, advanced civilizations would hide. They'd shield their gravitational signatures. They'd modify their warp geometries to minimize detectable emissions. They'd avoid populated regions of space to keep themselves secret. Maybe. Probably, even. But even the most careful civilization leaves traces. A single unshielded jump. One emergency maneuver. A primitive warp drive from their early experiments, crude and loud and impossible to hide. We only need one clear signal, just one. And the search is just beginning. Imagine this. A signal arrives. Not from a radio telescope pointed at the stars, but from the very fabric of space itself. A gravitational wave, unmistakable and impossible to ignore. And encoded in its ripples is the fingerprint of something we have searched for our entire existence. Proof that faster-than-light travel is not just theoretical fantasy. It is real. It works. And someone out there is using it right now. This is not idle speculation. When a warp bubble tears through interstellar space, at velocities that defy everything we thought was possible, it leaves scars. Shock waves ripple outward. High-energy particles accelerate at the bubble's boundary, screaming out gamma rays and cosmic ray bursts. Like a lighthouse beam cutting through darkness, the light itself warps around the moving warp field, stretched and compressed into distinctive red and blue shifts that would stand out like a neon sign in the cosmic night. We should be seeing these signatures everywhere, yet the universe appears silent. Our telescopes sweep across the frequencies, our detectors listen intently, and they hear nothing. Not a single confirmed detection of an alien warp drive. Not yet, anyway. But here is the crucial part. Silence does not mean absence. We have only been seriously searching for a few years, armed with equipment that is, frankly, still quite primitive by cosmic standards. It is like sending a deaf person into a concert hall and asking them to report what they hear. The music might be thundering all around us. Now imagine that first moment of detection. That unambiguous signal arrives. In that instant, two of humanity's deepest questions get answered simultaneously. Are we alone in this universe? And can faster-than-light travel genuinely work? That single discovery would reshape everything we know about physics, rewrite our understanding of possibility itself, and potentially accelerate our own warp drive research by decades. We would know, with absolute certainty, that the universe permits this technology, that it is not forbidden by the laws of nature, that it is achievable. So the search continues. Every year, new detectors come online. Algorithms grow smarter. Analysis techniques become more refined. The net is tightening. If alien warp drives are out there, carving their signatures into the fabric of space-time itself, we will find them eventually. But here is where it gets truly fascinating. What happens after? What happens when we actually catch them? Reverse engineering alien technology sounds like pure science fiction. Until you realize humans have been doing this for centuries. When Europeans first encountered Chinese gunpowder, they did not need to understand the full chemistry immediately. They analyzed the mixture, experimented with ratios, and eventually reproduced it. The same story repeats throughout history, from steelmaking to semiconductors to jet engines. Each time, the pattern is identical. Observe the technology, analyze its outputs, reconstruct its inner workings. If we detect gravitational wave signatures from an alien warp drive, we get something extraordinary. Direct observation of a working model. The wave patterns would reveal everything: the bubble geometry, the energy distributions, the propulsion timing, the acceleration profiles. We could measure it all from the outside, even though we cannot peer inside the mechanism itself. It becomes an inverse problem. Computer simulations could model what configurations would produce those exact signatures. Given the output, calculate the input. This is not theoretical. Engineers use this approach constantly. Medical CT scans work exactly this way, reconstructing three-dimensional human anatomy from two-dimensional X-ray projections. From the outside in. A research team already laid the groundwork for this exact approach. They built a library of simulated warp signatures, so when real detections occur, algorithms can instantly match patterns to theoretical models. Think of it like facial recognition, but for warp drives. The system learns what different designs should look like, then identifies them in observational data. Of course, complications emerge. Some researchers worry about treaty violations, about galactic etiquette. If advanced civilizations are deliberately hiding their warp signatures, should we respect that privacy? Others counter that knowledge itself is not theft. We would not be stealing anything. We would not be attacking anyone. We would simply be learning from observations that anyone could theoretically make. Then there is the raw technological gap. An alien civilization using warp drives could be thousands of years ahead of us, millions of years ahead. Their fundamental understanding of physics might include principles we have not even discovered yet. Reverse engineering their technology could prove impossible if it relies on science that is simply beyond our current comprehension. But consider this alternative. The laws of physics are universal. General relativity works the same on their world as it does on ours. If they found a way to generate negative energy density, if they discovered how to manipulate space-time curvature itself, those mechanisms should ultimately be comprehensible to us. The mathematics might be brutally complex, but probably not incomprehensible. History suggests reason for optimism. We have cracked alien technologies before. We will likely crack this one too. And when we do, everything changes. When ancient ingenuity meets the cosmic mystery. 2,000 years ago, a ship sank off the Greek island of Antikythera. Among its cargo, a bronze machine so impossibly intricate, so bewilderingly advanced, that when divers recovered it centuries later, scientists couldn't believe what they were looking at. Gears within gears. Precision engineering that shouldn't have existed for another 1,000 years. We call it the Antikythera mechanism, and it took us decades to truly understand it. But here's what matters. Each piece we deciphered accelerated our understanding of the next. Knowledge doesn't grow in a straight line. It compounds. It explodes outward. Now imagine finding something similar in the night sky. Not a sunken relic, but a signature. Proof that somewhere out there, an alien civilization cracked a problem that still eludes us. Faster than light travel. The Holy Grail. Detect even one confirmed warp signature, and everything changes overnight. We wouldn't need theories anymore. We wouldn't need debates about whether the physics works. The universe itself would hand us the answer. It's possible. Someone did it. That single confirmation would be worth more than any Nobel Prize. Governments would mobilize. Private companies would pour unlimited resources into research. Within months, perhaps days, the race would begin. a global scramble to reverse engineer alien technology. The organization or nation that cracked it first wouldn't just become powerful. They'd become everything. Geopolitically, economically, militarily. They'd reshape human civilization. But here's the terrifying part of that dream. The dark side of discovery. What if those signatures tell us something we don't want to know? What if warp bubbles don't just bend space? What if they wound it? What if each jump tears a microscopic scar through the fabric of spacetime itself? Scars that accumulate, that spread, that eventually catastrophically destabilize reality in ways we can't predict or control. Maybe that's why we haven't detected warp signatures in our cosmic neighborhood. Maybe it's not that aliens haven't discovered the technology. Maybe they have. And maybe they've learned the hard way that using it carries a price too terrible to pay. Perhaps entire civilizations have abandoned certain regions of space, haunted zones where warp drives have left reality fractured and broken. Still, the potential reward overwhelms the risk. Imagine, instead of centuries of dangerous experimentation, trial and error, failed prototypes, and catastrophic accidents, we could learn from their success. We could skip straight to proven designs. We could compress millennia of research into decades. Unless, of course, they're already watching us. The paradox that breaks reality. Here's why some physicists have genuine nightmares about faster-than-light travel. It doesn't just move you quickly, it moves you backward in time. Einstein showed us that speed and time are entangled. Push something fast enough relative to certain observers, and those observers see it arriving before it left. You've crossed the speed of light barrier, and when you do, causality fractures. Enter the grandfather paradox. You build a time machine. You travel back. You prevent your grandfather from ever meeting your grandmother. Your parents never exist. You're never born. But if you were never born, you never went back in time. So your grandfather does meet your grandmother. So you are born. So you do go back. And around, forever. An infinite loop with no consistent ending. Reality doesn't allow this. It can't. If effects can come before causes, if you can receive an answer before asking the question, if you can die before you're born, then nothing, absolutely nothing, makes sense anymore. Some physicists concluded, the universe must forbid it. Faster than light travel is impossible, because it would destroy logic itself. The cosmic immune system. Stephen Hawking had a different theory. He called it the chronology protection conjecture. The idea, unknown physics, quantum mechanics, something we haven't discovered yet, acts like an immune system for reality itself. Whenever conditions threaten to create a paradox, whenever causality is about to snap, something intervenes. A barrier rises. The attempt fails. The universe protects its own consistency. But other physicists discovered something unexpected. Warp drives might naturally sidestep the paradox problem entirely. Here's why. Inside a warp bubble, nothing moves faster than light locally. The space around you doesn't accelerate you beyond light speed. Instead, the fabric of space-time itself compresses in front of you and expands behind you. You're surfing on a wave of warped space. From your perspective inside the bubble, you never break light speed. More than that, the bubble insulates you, isolates you. Information from inside can't propagate outward in a way that creates backward-in-time effects because the bubble's unique geometry seals off that possibility. It's like being wrapped in a protective shell that the laws of causality cannot penetrate. The question that haunts us. We may never know if nature allows warp drives or forbids them. We may discover the technology works beautifully, Or we may find that the universe has a deeper law we haven't uncovered yet. A law that makes faster than light travel fundamentally impossible, no matter how clever we become. But there's one scenario that keeps physicists awake: that we find the signal, that we decode it, that we learn, definitively, that aliens mastered warp technology and used it to visit the stars, and that they've been watching us all along, waiting to see if we're ready for what comes next. The universe's firewall against time travel. Imagine a bubble, a pocket of warped spacetime that lets you slip faster than light. Powerful idea, terrifying problem. Any signal trying to cross that bubble's boundary faces a choice: obey the laws of physics or create a paradox. The bubble acts like a wall, not to keep you in or out, but to keep causality intact. It's the universe's security system, preventing information from flowing backward in time in ways that would unravel reality itself. But there's another problem. Warp drives don't run on wishes. They demand continuous energy, fusion reactions, antimatter explosions, power that has to flow now in real time. You cannot retroactively feed energy to a bubble that has already collapsed. The physics doesn't work backward, and that temporal directionality, that one-way arrow of cause and effect, might be exactly what saves us from time travel paradoxes. You move faster than light, sure, but you still cannot escape the tyranny of now. Some physicists propose an escape route. What if the universe has a loophole? When you travel back in time and change the past, you don't destroy your original reality. You branch it. You create a new timeline, splitting off from that moment. Your old world keeps existing. You just can't go back to it. You visit parallel versions, where history unfolded differently. No contradictions. No grandfather paradoxes. Just infinite universes, infinitely branching, like a tree growing sideways through reality. Quantum mechanics hints that something like this already happens. Every time a particle is measured, every time nature makes a choice, the universe might be splitting. Warp travel could simply make those branches accessible to us. The honest truth? We don't know. We're speculating about technology that doesn't exist, using theories that are still incomplete. We've never achieved faster than light travel. We've never tested whether causality collapses or survives. But here's what's certain. The moment we build a working warp drive, we'll get answers. Either paradoxes emerge, revealing new physics we've never imagined, or they don't. Either outcome is revolutionary. The universe either has built-in protections we haven't discovered, or it permits time travel in ways that don't break reality. Both possibilities rewrite everything we know. The fear of paradoxes should not stop us. Yes, scientists have obligations to be careful, but we also have obligations to know what reality permits. If warp drives ultimately prove impossible, if causality truly cannot be violated, that itself would be one of the most profound discoveries in human history. It would tell us something fundamental about the structure of existence itself. But there's another reason faster than light travel seems cruel, even if paradoxes don't matter. Einstein's equations contain a hidden punishment: time dilation. The faster you move through space, the slower you move through time. Not metaphorically, literally. At 99% of light speed, time doesn't just slow down a little. It slows down 7 times over. A 10-year journey from your perspective? 70 years pass on Earth. You step out of your spacecraft barely aged. Your friends are elderly. Your children are older than you. Society has transformed beyond recognition. Everyone you knew is gone. You've become unstuck in time, living a paradoxical existence where your heartbeat marches to a different rhythm than the rest of civilization. The isolation is profound and irreversible. The twin paradox makes this visceral. Two identical twins. One stays on Earth. The other blasts off at near light speed and returns. The traveling twin is younger, biologically younger. Their cells divided fewer times. They experienced fewer heartbeats. This isn't a trick of perception. It isn't an illusion. Time genuinely flowed at different rates. Particle accelerators prove it every single day. Unstable particles that should decay in microseconds keep ticking along when accelerated to 99% of light speed. Their internal clocks slow down. The universe doesn't care that it seems bizarre. The math works. The predictions match observations. Reality enforces these rules with absolute indifference. Imagine standing at the edge of the known universe, ready to cross an impossible distance. You pack your bags. You say goodbye to everyone you love. And you step into a spacecraft. By the time you arrive at your destination, a star 50 light-years away, a century will have passed on Earth. But here's the cruel twist. Thanks to time dilation, you might only experience 20 years. You'll land, step out of your ship, and discover that everyone you knew is dead. Your children are ancient. Your grandchildren have grandchildren. You've become unstuck in time, a ghost from the past, visiting a future that moved on without you. This is the temporal horror of conventional space travel. And humanity has only found two ways to escape it. The first is to accept the horror entirely. Generation ships. These are vessels so massive, so self-contained, that they function as moving cities. Multiple generations are born, live their entire lives, and die aboard them, all while traveling toward a star no one alive will ever reach. Sounds bleak, right? That's because it is. But at least everyone ages together. The problem shifts. Now you're trying to keep a civilization stable for centuries. You need these people to care about a mission their ancestors chose, to maintain technology they never invented, to stay focused on a destination they'll never see. One cultural shift, one technological setback, one leader with bad ideas, and the whole thing could collapse, leaving a broken, drifting ship full of people who never wanted this life in the first place. Then there's the other solution: warp drives. If they work, and that's still a massive if, they change everything. Here's why. A warp bubble doesn't actually move a spacecraft through space at relativistic speeds. The bubble itself warps the fabric of spacetime, carrying normal space and normal time inside it. You're not racing toward light speed. You're surfing on a wave of spacetime itself, and that changes everything. Inside the bubble, time flows at exactly the same rate as it does on Earth. You could travel to Proxima Centauri in weeks, turn around, come home, and find that only weeks have passed everywhere. Your spouse is still the age you left them. Your children haven't aged years, they've aged weeks. You step off the ship into the same era you left. Think about what that means. Your relationships stay intact. Your knowledge remains relevant. You don't become a temporal refugee, exiled from your own time by the laws of physics. But there's more. This makes interstellar travel economically possible. A corporation funding a mining operation needs returns within decades, not centuries. A government planning colonization can't wait generations for feedback. With warp travel, the timeline becomes human-scaled. It matches the way our institutions actually work, the way we plan, the way we live. And there's one more advantage, one that's almost boring until you think about it carefully. With time flowing consistently everywhere, causality stays intact. Cause leads to effect. Effects don't precede causes. You can't exploit time differences to create paradoxes. You can't send information backward through time by clever routing between reference frames. The universe stays logically consistent. Of course, all of this assumes warp bubbles actually work. If they have hidden side effects, if space-time behaves differently inside them than we predict, everything falls apart. But according to current theory, warp drives might offer something revolutionary: fast transportation without the temporal nightmare. But here's the thing about conventional propulsion. There's an even more immediate problem. More lethal, more visceral. Accelerating a human body to extreme speeds will kill you. Fighter pilots can barely survive 9 times Earth's gravity during extreme maneuvers. 9 times normal weight. That's the limit before consciousness fails. But reaching even 1% of light speed in a reasonable time frame requires sustained acceleration, thousands of times stronger than Earth's gravity. Your bones don't shatter. They pulverize. Your blood vessels don't just rupture, they explode. Your brain doesn't get crushed gently against your skull. The pressure is so intense, so instantaneous, that death is not suffering followed by death. Death is simply instantaneous. Science fiction writers have imagined solutions. Acceleration couches filled with liquid. Support that distributes pressure evenly across your entire body. But even that is just fiction brushing up against the edge of an engineering nightmare. Warp drives sidestep this too. Inside the bubble, you experience no acceleration at all. The space-time around you warps. You don't feel a thing. You don't need suspension, liquid support systems, or tranquilizers. You sit in a comfortable chair, read a book, and watch the universe reshape itself around you. No time dilation, no crushing acceleration, no generational sacrifice. Just travel. That's why, despite all the theoretical impossibilities, despite the energy requirements that seem to violate everything we know about physics, warp drives remain the most seductive dream in the human imagination. The crushing reality of speed. Here's the brutal truth about moving humans through space. Our bodies are fragile. Soft tissue and bone can only tolerate so much force. Push the acceleration hard enough, and physics turns your body into a meat grinder. A cushion helps. Padding distributes the force, but only up to a point. Once you hit hundreds or thousands of Earth gravities, the kind of acceleration you'd need for fast interstellar travel, no amount of padding saves you. The pressure becomes so extreme that your tissues liquefy. Your organs don't survive. You don't survive. Generation ships sidestep this problem entirely. They accelerate so slowly, so gently, that it takes decades just to reach cruising speed. Your body never experiences crushing forces because the acceleration spreads across years of almost imperceptible changes. It works, but there's a price. Centuries in transit. You're trading lethal acceleration for glacial speed. Maybe suspended animation could help. Freeze the travelers. Put them in stasis. Skip the centuries of boredom. Except we can't actually do that. When human tissue freezes, ice crystals form. Those crystals shred cells from the inside out. Cryogenic preservation has been chased by researchers for decades. It remains science fiction. And even if someone solved it tomorrow, there's another nightmare waiting. Thawing someone after that journey might just give you a thoroughly scrambled corpse. This is the meat grinder problem. It's a fundamental barrier. The physics doesn't care about our ambitions. The biology has limits that technology cannot overcome. You cannot accelerate human bodies fast enough to reach significant fractions of light speed within a single human lifetime. The universe has locked that door. But there's another way. A completely different approach. One that doesn't fight the problem, it erases it. The warp bubble solution. Imagine a spacecraft surrounded by a bubble of warped spacetime. Inside that bubble, something extraordinary happens. Nothing moves. The ship experiences zero acceleration, no crushing forces, no danger, no stress on fragile human bodies. This isn't magic. It's geometry. Here's how it actually works. The spacecraft inside the bubble doesn't accelerate at all. Space itself accelerates around you. You remain stationary. The cosmos reorganizes itself around your vessel, while you stay perfectly still. Your coffee doesn't slosh. Your stomach doesn't drop. Your body experiences no sensation whatsoever, because from your perspective, you're not moving. Inside the bubble, local spacetime remains completely flat and normal, the way it works here on Earth. The extreme curvature? That exists only at the bubble's edge. You live in an island of calm reality, while the universe bends around you. Here's where it gets almost impossible to grasp. You could theoretically accelerate from stationary to 10 times the speed of light instantaneously. Not gradually, instantly. And the people inside wouldn't feel a thing. No buildup, no crushing forces, no transition at all. Reality inside stays constant, while your relationship to everything outside transforms. What this actually means. This changes everything. Warp travel isn't just fast, it's comfortable, it's safe. Fragile equipment doesn't need special mounting. Delicate scientific experiments could run during transit. Passengers could walk around, eat meals, go about normal activities while traveling faster than light. The journey becomes routine instead of an endurance test or a death sentence. But the implications go deeper than comfort. You could transport anything that exists, living organisms, complex machinery, volatile chemicals, entire ecosystems. Imagine sending Earth life to another world. Plants, animals, microorganisms, all traveling together in a self-sustaining environment. With conventional propulsion, keeping such a system alive through decades of travel with violent acceleration phases seems nearly impossible. Organisms would be crushed, systems would fail, life would shatter. With warp drive technology, it becomes straightforward. Just maintain life support during what amounts to a brief, smooth journey. No trauma, no acceleration-induced death. The biology survives. Every problem that makes conventional interstellar travel nearly impossible simply vanishes inside a warp bubble. The speed without time dilation, movement without acceleration forces, travel without exotic life support or suspended animation. All of it solved. But here's the catch that haunts every physicist's dream. None of this matters if we cannot actually build one. The interior of a warp bubble would feel absolutely ordinary. You could not tell if the bubble was moving at 10 times light speed or sitting completely still. Physics inside operates exactly like physics on Earth, because the space-time inside remains flat and undistorted. Perfect, comfortable, and, for now, completely theoretical. Imagine this. You're inside a bubble, not a fragile one. A bubble of pure, untouched normality, carved out of space itself. Your watch ticks. Your cells age. Light moves at light speed. Every fundamental constant of physics stays exactly as it should be. You're not experiencing anything strange at all. But everything around you, the universe itself, is being warped, bent, twisted into a shape that propels you forward. You're surfing on a wave of space-time distortion, and inside your protective shell, you feel absolutely nothing. It's one of the most paradoxical concepts in physics. Complete normalcy, wrapped in complete madness. But there's a price. That extreme warping? It happens only at the boundary. And that boundary creates a barrier, an invisible wall between you and the rest of the universe. Try to send a radio signal outward. It has to cross that transition, where spacetime curves so violently that electromagnetic radiation might not survive the journey. Your message gets trapped. You become silent. Radio signals from Earth trying to reach you. Same problem. You're in complete blackout, cut off from home for days, maybe weeks. Mission Control has no idea what's happening to you. You have no idea what's happening to them. This isn't a minor inconvenience. This is the kind of isolation that changes how we think about space travel. Mission planners can't rely on real-time guidance from Earth. They can't radio home for advice. Ships need to carry complete autonomy. Every decision, every protocol, every contingency plan loaded before departure. You're not just traveling to another star. You're traveling into silence. And then there's what you see through the windows. Look ahead, and the light from distant stars reaches you, compressed, blue-shifted, forced into gamma rays by the contraction of space in front of your bubble. Everything ahead becomes a blur of violent radiation. Look backward, and the stars stretch and redshift into radio waves by the expansion of space behind you. The entire visible spectrum, the entire rainbow of light that normally fills the cosmos, collapses into a narrow ring at the horizon. Some physicists think you might not see anything at all through forward windows. The compressed space might create something like an event horizon. Light can't escape the warp field to reach your eyes. You fly blind, trusting only instruments, flying toward a destination you literally cannot see. Yet inside, everything is protected. The boundary shields you completely. Cosmic rays? Blocked. Interstellar dust that would pulverize a conventional ship? Harmless. Even a supernova exploding outside your bubble? You'd feel nothing. Not a degree of heat. Not a particle of radiation. The boundary is absolute. Inside, gravity is whatever you make it. The warp field doesn't create gravitational effects because space-time inside remains flat. Artificial gravity systems work normally, or nothing works, and you float, your choice. Fusion reactors hum. Power systems distribute energy. Antimatter containment stays stable. All the complex machinery that keeps a ship alive operates exactly as designed. The exotic physics, the reality-bending science, exists only at the boundary. Not here. Not where you are. But here's the thing nobody talks about: your mind. You're isolated inside a bubble of normal physics while the universe restructures itself around you. That's not just a scientific fact, that's existential. Some astronauts might find comfort in it, a safe haven, a pocket of sanity in cosmic chaos. Others will feel profound unease. You exist in a tiny pocket of reality, insulated from the larger universe, and you know it. That knowledge alone can be destabilizing. Psychological training becomes as critical as engineering protocols. Routines matter. Keeping your mind stable matters. Because for weeks, you're cut off from everything you know. But think about the alternative. Imagine spending decades in a conventional spacecraft, crawling between stars at sublight speed, watching everyone you left behind age normally while you age slower, returning to a world centuries older than you are. Now compare that to a few weeks in discomfort inside a warp bubble. The choice becomes clear. Yes, the isolation is unnerving. Yes, the psychological challenges are real. But the physics advantages? They're revolutionary. For the first time in human history, we could reach other stars within a single human lifetime. Not as ancient explorers, barely aging while everyone else moves on. As people, as crews, returning home to a world that barely changed while we were gone. That's not just a technological breakthrough. That's the difference between interstellar travel and the dream of interstellar travel finally becoming real. The secret race to break physics. Deep in Building 9 at NASA's Johnson Space Center in Houston, something extraordinary was happening, and almost nobody knew about it. For years, Harold White's team operated in the shadows. Officially, they were studying exotic propulsion concepts. That's what the budget requests said. That's what the public records showed. But the real work? They were chasing something far more ambitious. They were trying to build a warp drive. Think about what that means. Not incrementally faster rockets, not clever trajectory calculations, but the ability to bend space itself, to create a bubble around a spacecraft and ride it through the cosmos faster than light should ever allow. It sounds like fantasy. It sounds like science fiction. But these weren't dreamers. They were physicists, and they were building machines to measure it. Specialized equipment designed to detect nanoscale ripples in space-time. Capacitors arranged in configurations to amplify the Casimir effect. That strange quantum phenomenon where empty space isn't empty at all, where virtual particles flicker in and out of existence. Simulations running day and night, exploring the geometry of hypothetical warp bubbles. Every experiment was carefully designed. Every result was carefully documented. And every word was carefully chosen when outsiders asked questions. Then came 2021. Someone announced they'd detected warp bubble signatures in the lab. The secret was out. Suddenly, NASA had to choose. Deny everything and look foolish, or admit the truth and face the firestorm. They chose a third option. Confirm the research while downplaying its significance. Yes, we're studying this. No, it won't work for decades, maybe centuries. Don't get your hopes up. But behind closed doors, something different was happening. Funding increased, not decreased, increased. More physicists were recruited. Equipment orders expanded. The lab that barely existed on paper suddenly had multiple research tracks running in parallel. One team dug deeper into the Casimir effect itself. Another explored metamaterials, artificial structures engineered to manipulate the vacuum energy that permeates empty space. A third investigated whether quantum entanglement, that spooky connection between distant particles, could somehow warp space-time itself. And it wasn't just Houston anymore. Glenn Research Center in Ohio contributed its propulsion expertise. Jet Propulsion Laboratory in California brought advanced engineering. Ames Research Center added computational modeling. The research network quietly spread across the country, each facility tackling different pieces of an enormous puzzle. A distributed intelligence. A secret collaboration hidden in plain sight. But here's where it gets darker. Some of this research doesn't exist in the public record at all. It happens behind security clearances, in classified programs, in facilities where ordinary scientists never go. The breakthroughs that matter most, the ones that actually work, those might be locked away right now, invisible to civilian eyes. We might not hear about them for decades, maybe never. And we're not alone in this race. The military understands the implications perfectly. Faster than light travel isn't just about exploration. It's about dominance, about power. The first nation to weaponize warp drive would reshape geopolitics in ways we can barely imagine. So the Department of Defense is almost certainly funding parallel research. The Department of Energy, too. They have the plasma physicists, the fusion reactors, the particle accelerators needed to generate the exotic matter this technology would require. This is where the tragedy emerges. Scientists worldwide are probably working on the same problems. In Russia, in China, in Europe, in Japan, duplicating efforts, struggling with identical challenges that could be solved faster through collaboration, but they can't collaborate. Geopolitical fear prevents it. Security concerns lock it down. No one wants to hand potential adversaries a technological advantage that could reshape warfare itself. So the research proceeds in darkness. Hints leak out at conferences. Anomalies get mentioned in presentations. Patent applications describe exotic spacetime manipulation using deliberately vague language. Insiders whisper to journalists. The truth fragments into rumors and speculation. We're standing at a threshold. Humanity might be on the verge of achieving something that violates everything we thought we understood about physics. And we're doing it in secret, divided, competitive, unable to share the knowledge that could accelerate us toward a future where the limitations of distance no longer confine us. The warp drive research continues, in the light, in the shadows, somewhere between public science and classified secrets. We might already be building the technology that will take us to the stars. We just don't know it yet. The secret race for faster-than-light travel. Listen carefully. The most remarkable thing about warp drive research isn't what scientists say in public. It's what they don't. Walk into a conference room where physicists gather, and you'll notice something peculiar. The talks are meticulously choreographed. Researchers discuss breakthrough findings while carefully stepping around classified details, like dancers avoiding invisible tripwires. They signal through implications. They hint through omission. And between the lines, a very different story emerges. Publicly, NASA insists warp drives remain distant dreams. 50 to 100 years away, they say. Maybe longer. It's the safe answer. The conservative estimate. The official position that protects funding and credibility. But ask the right questions privately, and some researchers lean in closer. They whisper different timelines. They suggest that critical breakthroughs could arrive far sooner, if the right problems get solved, if the funding stays committed, if the pieces finally align. So what's real? The answer likely lives in the space between those two timelines. It could hide classified progress, invisible to the public eye, or it could simply reflect the eternal gap between how governments talk and how scientists actually think. What seems certain, what demands our attention, is this. Serious, well-funded research continues right now at multiple government facilities. They're deploying increasingly sophisticated equipment. They're refining advanced techniques, and that represents a seismic shift in how we approach the impossible. Warp drives didn't just jump from Star Trek to legitimate physics. They made that leap while we weren't paying attention. Government agencies now fund what was once pure fantasy. That's not speculation. That's transformation. But here's where it gets interesting. Government labs aren't alone anymore. Elon Musk rarely talks about warp drives in public. He has bigger stage moves to make. But SpaceX's actual long-term vision tells a different story. Establish self-sustaining cities on Mars. Check. Then what? Keep going. Keep reaching. Because Musk has made one thing abundantly clear. Making humanity a true multiplanetary species doesn't end with Mars. It demands reaching other star systems. Eventually. SpaceX doesn't employ thousands of ordinary engineers. It employs some of the world's best propulsion specialists and theoretical physicists. They work across sprawling facilities in Hawthorne, Boca Chica, and Cape Canaveral. Advanced laboratories built for cutting-edge research that hasn't been dreamed of yet. The company's entire culture runs on moonshot thinking, rapid prototyping, the willingness to pursue what everyone else calls crazy. If any private organization would seriously pursue warp drive research, SpaceX sits at the top of that list. The specifics? They stay locked away. SpaceX guards proprietary research like nuclear secrets. They reveal only what benefits them strategically. But job postings occasionally slip through the cracks. They're hiring plasma physicists, quantum field theory specialists, engineers steeped in general relativity, all recruited for advanced projects. No other details, no transparency. Equipment purchases tell their own story. Specialized sensors, high-energy systems, devices with no obvious connection to conventional rocket development. They accumulate quietly, building something. Rumors persist about test facilities in remote locations. Secret research tracks exploring physics beyond what chemical rockets can achieve. Former employees, bound by non-disclosure agreements that silence them, hint at research into spacetime manipulation. One anonymous source mentioned exactly that. Verification proved impossible. But the whisper remains. Consider the bigger picture. Musk's other companies could contribute in ways nobody expects. The Boring Company understands underground construction at scale, perfect for building shielded facilities that contain dangerous, high-energy experiments away from prying eyes. Tesla's battery and power management systems could enable the precise energy control that warp field generation demands. Neuralink's brain-computer interface work might help manage the staggeringly complex calculations required for real-time warp field manipulation. And then there's the money. Musk's personal wealth and the resources flowing through his companies dwarf most government research budgets. SpaceX alone generates billions from Starlink satellites and NASA contracts. Billions that could fund speculative physics research if Musk decides the potential payoff justifies the investment. History shows he makes those bets. He's wagered on technologies everyone dismissed as impossible. He's funded long shots because he believed they mattered. So the question isn't whether SpaceX could pursue warp drive research. It's whether they already are. But SpaceX isn't the only private player in this game. Jeff Bezos runs Blue Origin with a vision remarkably similar to Musk's: expanded human presence throughout space. Bezos employs talented engineers and physicists with access to substantial resources. Blue Origin presumably conducts similar research, explores similar possibilities. The picture that emerges is this: while the public watches conventional rockets launch, a parallel effort churns in the background. Government facilities continue rigorous theoretical and experimental work. Private companies with virtually unlimited resources explore exotic propulsion concepts. The barriers between what's classified and what's speculative blur into irrelevance. We may be watching the opening moves of a race nobody officially acknowledged started. Our final text. Right now, across the globe, something extraordinary is happening in the shadows. While SpaceX captures headlines with their Glenn rocket and lunar landers, generating revenue, building public support, other players are moving in silence. Lockheed Martin, Boeing, Northrop Grumman. These aerospace titans maintain hidden divisions dedicated to something far more radical: exotic propulsion systems that could rewrite the laws of physics. They operate with far less fanfare than SpaceX. But make no mistake, they're chasing the same holy grail. And they have advantages the private space company doesn't. Defense contracts grant them access to classified research. Government funding flows to their speculative projects with fewer questions asked. The barriers between public and private are blurring. But that's just the beginning. Silicon Valley billionaires have discovered that space exploration is no longer the exclusive domain of government agencies. Yuri Milner is funding the impossible. Through his breakthrough initiatives, he's sponsoring the search for alien life and something even more audacious: interstellar probes. Breakthrough Starshot aims to send tiny, laser-propelled spacecraft to Alpha Centauri, traveling at 20% the speed of light. Let that sink in. 20% of light speed. These are people willing to bet billions on revolutionary propulsion. And here's what's fascinating. Private companies move faster than government bureaucracies. They take bigger risks. They iterate without endless committees approving every decision. No classification restrictions slow them down. But they sacrifice something crucial: institutional knowledge, vast research facilities, decades of collaborative networks that government laboratories possess. The ideal situation: public and private working together. But intellectual property wars and security classifications make that nearly impossible. What remains crystal clear is this: multiple well-funded organizations, beyond NASA, beyond traditional aerospace, are actively researching faster-than-light propulsion. The race is on, conducted mostly in secrecy. Whoever achieves the first breakthrough will either become incomprehensibly wealthy and powerful, or spark a new era of space exploration that transforms humanity forever. Possibly both. But here's the critical question: which approach will work first? 3 distinct warp drive concepts have emerged as the most promising. 3 different paths to the same destination. Each tackles the same fundamental problem: how do you bend spacetime in ways that enable faster-than-light travel without requiring impossible materials or infinite energy? The Alcubierre drive is the most famous, and for good reason. Imagine a bubble surrounding your spacecraft. Space contracts in front of you, compressing, crushing inward. Behind you, space expands violently outward. Together, they create a wave, and that wave carries you forward. Harold White and others have run the numbers and discovered something remarkable. Recent optimizations have slashed the energy requirements dramatically. The challenge is no longer purely theoretical, it's engineering. The problem: you need exotic matter, negative energy density. You need to generate it at scales large enough to envelop an entire spacecraft. Current research focuses on one specific phenomenon: the Casimir effect. Quantum fields between parallel plates create tiny forces, small, negligible on their own. But what if you could amplify them? Think of an opera singer shattering a wine glass. The voice produces sound waves, tiny vibrations. But those vibrations resonate. They reinforce each other, amplify each other, and suddenly the glass explodes. What if you could do the same with Casimir forces? Create standing waves of negative energy density that cascade and reinforce themselves. The total effect might actually reach useful scales. Then there's the Notario drive. This approach improves on Alcubierre's instability problem. Instead of sharp boundaries between warped and normal space, boundaries that demand intense energy concentrations, the Notario drive distributes the warping smoothly across larger volumes. Think of the difference between a cliff edge and a gentle slope. One requires massive force to maintain. The other, it naturally wants to exist. Here's where it gets interesting. The Notario drive might not require exotic matter at all. Researchers at universities worldwide are exploring whether carefully shaped electromagnetic fields could generate the necessary energy density gradients, or plasma configurations, the same superheated matter we use in fusion reactors. These systems could create Notario-style warp fields as an almost accidental side effect. The plasma itself provides the energy variations needed to curve spacetime. The challenge is precision. Controlling plasma at the atomic level with the exactness required seems almost impossible today. But almost is the operative word. Research is advancing. And then there's the approach that rarely sees daylight. A third concept, less publicized, potentially revolutionary. One that doesn't try to create exotic matter at all. One that doesn't engineer warp bubbles from electromagnetic plasma. Instead, it exploits dark energy directly. The invisible force that accelerates the expansion of the universe itself. Picture this. 70% of everything that exists in the universe is completely invisible to us. We can't see it, touch it, or even hold it in our hands. Yet we know it's there because we can watch it tear the cosmos apart. That invisible force is dark energy, and it's been pushing galaxies away from each other with increasing violence for the last few billion years. Stranger still, dark energy has the exact same strange properties that physicists think warp drives would need. Negative pressure, the ability to warp the fabric of space itself. Here's the tantalizing possibility. What if we could reach into the void and grab that dark energy? What if we could concentrate it, bend it to our will, and use it as fuel? We could skip the exotic matter we don't have. We could forget about amplifying the Casimir effect. We could tap into an infinite energy source already woven into every cubic inch of space. There's just one problem. We have absolutely no idea what dark energy is. We don't know where it comes from. We can't predict what it will do. We only know it exists because we watch its fingerprints on the universe, pulling galaxies farther apart at accelerating speeds. Controlling something you don't understand? That requires a revolution. In physics, we haven't had yet. But researchers aren't betting everything on dark energy alone. Some are thinking bigger. They're building hybrid designs, combinations pulled from multiple approaches at once. Take the efficient bubble geometry from Alcubierre. Blend it with the smooth, stable boundaries from Notario. Then fuel the whole thing with dark energy manipulation. Mix different pieces from different models. See what sticks. The question becomes, what works? And that's where supercomputers come in. Millions of simulations run constantly in facilities around the world. Each one tests a different shape for the warp bubble, different energy distributions, different field configurations. Researchers are essentially throwing darts at a cosmic dartboard, hoping one lands in a zone that actually functions. It's methodical. It's exhausting. But it's not random guessing. Each failed simulation teaches them something. Each tiny success suggests a path worth walking down further. The process mirrors drug discovery. Scientists test countless molecular combinations, hoping to find one compound that produces the right effect. Most fail. A few show promise. You follow those threads deeper. But here's where the challenge gets real. No one has actually built the equipment to test any of this in a laboratory yet. Simulations are cheap. Reality is brutal. To measure space-time distortions on a nanoscale, to actually see the fabric of space bend even slightly, you need instruments that barely exist. We're talking about technology at the absolute bleeding edge of what's possible right now. And that's just for detecting changes at a billionth of a meter. If we wanted to create distortions at millimeter scales, we'd need entirely new apparatus. Equipment we haven't invented yet. Progress is slow, but it's real. Every single laboratory success, no matter how small, proves that another piece of the theory actually works. Each confirmation is a stepping stone. The field is crawling forward, inching its way from pure speculation towards something that might actually be engineered. And here's what makes it all so fascinating. We don't know which approach will win. Different research groups are pursuing different strategies. some betting on Alcubierre's model, others on Notario's. Still others exploring completely different ideas we haven't even talked about yet. This competition drives innovation. The diversity increases the odds that someone, somewhere, will stumble onto a configuration that actually functions. But every single approach, no matter how clever, crashes into the same wall: understanding space-time itself. For centuries, we thought the universe was like clockwork. Particles had exact positions. Forces followed simple mathematical rules. If you knew where everything was right now, you could calculate exactly where it would be tomorrow. Deterministic, calculable, predictable. Then quantum mechanics arrived and burned that comfortable worldview to ash. At the microscopic level, the universe doesn't work that way at all. Particles don't have exact positions. They exist as probability clouds, fuzzy and undefined. They're waves and particles at the same time. The moment you try to measure where one is, you make its speed unknowable. The more precisely you pin down its location, the more its motion becomes a complete mystery. The universe isn't clockwork. It's probability. It's randomness. It's gambling with the fabric of reality itself. But here's where it gets truly weird. Empty space isn't actually empty. According to quantum mechanics, virtual particles are constantly blinking in and out of existence everywhere, all the time. They borrow energy from quantum uncertainty itself, exist for the briefest possible instant, then vanish and repay that borrowed energy before the universe even notices. Everywhere you look, in your room, in outer space, inside your body, this quantum foam is churning. This seething sea of creation and annihilation underlies all of reality, and we can actually measure it. We can prove it's real. The Casimir effect shows us directly that this invisible quantum foam exerts real forces on the world. That's the universe we're trying to manipulate. That's the physics we're trying to master. Not the old clockwork universe of centuries past, but something far stranger. Something built on probability, on virtual particles, on the permanent uncertainty woven into existence itself. To build a warp drive, we don't just need better technology. We need to understand reality at a level deeper than we currently do. Picture two metal plates separated by nothing but empty space. They shouldn't attract each other. Nothing is pushing them together. Yet they do. They pull toward one another with measurable force. This is the Casimir effect, and it's a window into a truth that shatters everything you thought you knew about reality. The vacuum isn't empty. It's seething. Beneath the surface of nothingness, quantum particles constantly flicker into existence and vanish just as quickly. These ghost particles create energy imbalances, ripples in the fabric of space itself. Those metal plates, they're being crushed together by the weight of these invisible fluctuations. Welcome to the microscopic universe, where the rules don't just bend, they shatter. This weirdness isn't a bug in reality. It's the foundation, and warp drives depend on exploiting it. Here's the dream. Imagine reshaping space-time itself. Compress the fabric of reality in front of you, stretch it behind you, and you slip through the universe without ever exceeding light speed. You haven't broken Einstein's law. You've rewritten the playing field. But there's a catch. To pull this off, you need regions of negative energy density. You need to manipulate the quantum vacuum with precision we've never achieved. You need to make quantum effects work at scales and intensities 1,000,000 times beyond anything we can currently control. The problem? Quantum effects are inherently tiny and fleeting. A ghost particle blinks into existence for trillions of a second and vanishes. We need to make these microscopic whispers roar. We need them to persist. We need them to do useful work, on a scale we can actually engineer with. Quantum field theory gives us the equations, beautiful mathematics that describes how these phantom energies behave. But here's the brutal truth. We can write the equations, but we cannot solve them. The moment you introduce curved spacetime and gravitational fields, the math becomes impossibly complex. Supercomputers crunch away at simplified versions and still hit walls. The gap between what we theoretically understand and what we can practically build is measured not in years or decades, but in centuries. It's like the 1800s and the dream of powered flight. Everyone knew the physics. Hot air rises. Wings create lift. But building something that actually flies? That was a different beast entirely. We're in that same position with warp drives. The physics exists. The engineering wisdom does not. But then came quantum computers. These machines don't just process information faster. They think differently. They exploit the same quantum weirdness that makes warp drives possible. Superposition, entanglement, probability clouds. A quantum computer could potentially simulate quantum vacuum effects and space-time curvature far more efficiently than classical computers ever could. If we can accurately model what happens inside a warp field using quantum computers, we might discover configurations that classical physics completely misses. Hidden pathways that mathematics alone could never reveal. And there's something else stirring in the darkness. Entangled particles are connected. Measure one, and you instantly influence the other, no matter the distance between them. Einstein hated this idea. He called it spooky action at a distance because it seemed to mock the universal speed limit. Yet experiments keep confirming it's real. No information travels faster than light. The universe is careful about that, but the correlation is undeniable and instantaneous. Some physicists are beginning to ask, could entanglement unlock something about warp drives? Imagine entangled quantum states spanning the boundary of a warp bubble. Imagine using entanglement to coordinate quantum vacuum manipulations across vast distances, creating coherent warp fields where none should exist. Some theorists suggest this might be possible. Others say it's pure speculation, bordering on fantasy. But here's the thing about quantum mechanics. It has a history of making the impossible real. Throughout the 20th century, physicists dismissed ideas as absurd, only to watch them become reality. Superposition, tunneling, quantum teleportation. Each seemed to violate common sense. Each turned out to be true. Reality operates on principles far stranger than intuition can grasp. The universe fundamentally follows probabilistic rules. No certainties, only probabilities and waves of possibility. Moving from classical to quantum thinking isn't just a scientific shift, it's a philosophical one. We have to accept that the world works differently than our senses tell us it does. Warp drives force us even deeper into this quantum realm. They demand we learn to engineer ghost particles and uncertain properties with the same precision we now engineer electronics and mechanics. That might take decades, it might take centuries, but the payoff extends far beyond faster than light travel. We're talking about entirely new technologies built on manipulating the quantum substrate of reality itself. We stand at the threshold now. The key to unlocking this new era of physics might already exist. It's hidden in the data we haven't analyzed, in the equations we haven't solved, in dark energy itself. One of the deepest mysteries the universe has ever posed. Somewhere in that darkness, the answer waits. We just have to find it. Imagine standing at the edge of everything we know about the universe. Expand your gaze across billions of galaxies, each containing billions of stars. They should be slowing down. Gravity should be pulling them back. But they're not. They're accelerating. speeding up, flying apart faster and faster into the cosmic void. Something is pushing them. We call it dark energy, and it comprises 70% of everything that exists. Every atom in your body, every star, every galaxy, every particle of light, they account for just 30% of reality. The rest? A mystery we cannot see, cannot touch, cannot directly measure. Dark energy is the universe's secret, hidden in plain sight. But here's where it gets fascinating. Dark energy doesn't pull things together like gravity does. It pushes them apart. It exhibits negative pressure, a force that repels rather than attracts. And this property has a haunting parallel to something physicists have theorized for decades: warp drives. You see, warp bubbles require exotic matter with precisely this kind of negative pressure to warp space-time around a spacecraft. The problem? We've never found exotic matter. We don't know how to make it. The energy requirements seem impossible, but dark energy already provides exactly what we need. It's everywhere. Right now, this very moment, you're immersed in it. Every cubic meter of empty space around you contains dark energy. The universe has handed us an infinite fuel source with the exact properties required to make warp drives work. We just need to learn how to use it. The question, of course, is how. Current physics can't explain where dark energy comes from or why it has negative pressure. Some physicists think it's woven into the fabric of space-time itself, a cosmological constant representing the inherent energy density of the vacuum. Others propose it's a dynamic quantum field, slowly evolving across billions of years. Nobody knows for certain. But here's the thing. Humans have harnessed powerful forces before understanding them completely. Ancient civilizations used fire for thousands of years without knowing about oxidation chemistry. Farmers selectively bred crops for 10,000 years before genetics even existed as a science. Practical application often comes first. Understanding catches up later. What if warp bubbles tap into dark energy by accident? When you warp space-time around a spacecraft, you create intense curvature at the bubble's boundaries. Those extreme distortions might naturally interact with the dark energy permeating that region. The bubble could draw fuel from the same mysterious force that's accelerating the universe's expansion. Elegant, efficient, already provided by nature. Some theoretical models suggest that intense space-time curvature could alter how dark energy behaves locally. You could create conditions where dark energy exhibits even stronger negative pressure. That amplification might generate the warp effect itself. And there's another intriguing possibility: quantum vacuum energy, the same force behind the Casimir effect, where two metal plates experience an attractive force from empty space, might actually be related to dark energy. Both involve energy densities in apparently empty space. Both defy classical physics. Understanding one might illuminate the other. Learning to manipulate vacuum energy at useful scales could simultaneously teach us to manipulate dark energy. But there's a monumental obstacle standing in our way: detection. We know dark energy exists because we see its fingerprints across the cosmic expansion. But detecting it locally, with our current instruments? It's impossible. Imagine trying to measure tiny ripples in water while standing in the middle of the ocean. The local fluctuations disappear in the cosmic noise. We need sensors sophisticated enough to measure dark energy density variations in laboratory settings, a technical hurdle of staggering proportions. Yet researchers are proposing solutions. Gravitational wave detectors might hold the key. Warp bubbles should produce distinctive gravitational wave signatures. Dark energy fluctuations likely would too. The next generation of advanced detectors, coming online over the next decade, might finally achieve the sensitivity needed to measure these effects. We stand at a threshold. The fuel is all around us. We're learning to detect it. And within a century, what seems like pure science fiction today might become the machinery of tomorrow. The hidden architecture of reality. Imagine you're standing at the edge of the universe's greatest mystery. Dark energy, the force that makes up nearly 3/4 of all existence, remains almost completely unknown to us. We can measure it. We know it's pushing everything apart, but we have no idea what it actually is. Now imagine this. What if dark energy isn't just some cosmic background force? What if it pools and concentrates in certain regions? What if it swirls around black holes and neutron stars in ways we haven't yet discovered? The universe might already be showing us how to manipulate this mysterious substance. We're just not paying attention yet. This is where things get wild. If we could harness dark energy, if we could learn to bottle it and use it, everything changes. Warp drives wouldn't be impossible anymore. They'd go from violates the laws of physics to extremely difficult engineering problem. The fuel we need might already exist. We just have to figure out how to pump it. But here's the thing. To use dark energy, we need to understand something far stranger about reality itself. For over 100 years, Einstein gave us a beautiful picture of the cosmos. Space and time aren't separate things. They're woven together into a fabric. Space-time, massive objects create dents in this fabric, like bowling balls on a trampoline. When things accelerate, they send ripples radiating outward, gravitational waves. It's elegant. It works. It explains nearly everything we observe. But what if it's incomplete? What if space-time isn't smooth at all? Quantum mechanics whispers something unsettling. At the smallest scales so tiny they make atoms look enormous, space-time starts to fall apart. We're talking about the Planck length, 10 to the minus 35 meters. Below that threshold, the universe stops cooperating with our mathematics. Quantum fluctuations erupt. The very concept of smooth, continuous space becomes meaningless. Think of it like a photograph. From across the room, it looks perfectly smooth and continuous. But zoom in far enough, and you see pixels, grainy little blocks of information. Reality might work the same way. Space-time could be pixelated at the quantum scale, held together by discrete, fundamental units. Not smooth, not seamless. And this matters because seams are weak points. Tailors know this. When you want to cut fabric, you don't fight against the weave. You cut along the grain where the fibers naturally part. What if space-time works the same way? What if there are places where the fabric is already thin, already strained? Where bending or stretching, it requires less energy. The strongest candidates? Black holes. An event horizon isn't just some theoretical boundary. It's a scar in space-time, a place where physics stops pretending to be continuous and reveals its true nature. Cross that boundary, and everything inverts. Space and time swap roles. Your future points toward the singularity instead of toward tomorrow. Escape becomes impossible. Time itself becomes a one-way street. This is what makes black holes so terrifying and so fascinating. They're natural laboratories where space-time is twisted to its absolute limits. And from that extreme warping, something impossible happens. Hawking radiation. Virtual particles emerge from the quantum foam at the event horizon. Gravity is so intense here that it tears apart particle-antiparticle pairs before they can annihilate. One particle gets pulled inside. The other escapes, carrying energy away from the black hole. The universe is literally extracting energy from the fabric of space-time itself. If we could understand that mechanism, if we could replicate those extreme quantum effects artificially, we might be able to create artificial seams in spacetime, boundaries where the rules shift, places where warp bubbles could operate. Then there are wormholes. If they exist, they're the ultimate seams. Direct shortcuts through spacetime itself, tunnels connecting distant regions. According to theory, wormholes require exotic matter to hold them open, the same impossible material that warp drives demand. But what if that's not actually a coincidence? What if a warp bubble is really just a mobile, self-contained wormhole? A pocket of normal space traveling through a tunnel of warped spacetime that surrounds it. We don't have to stop there. String theory suggests spacetime has more dimensions than we can perceive. There are dimensions beyond the three we navigate, and the one dimension of time we're trapped in. Extra dimensions, curled up so tightly at every point in space that we've never directly detected them. But string theorists wonder, what happens when spacetime gets twisted to its breaking point? What happens near the boundaries of black holes or at quantum scales? Could these hidden dimensions suddenly become accessible? Some physicists push even further. They ask, what if spacetime itself isn't fundamental? What if it emerges from something deeper? The way water molecules, individually invisible, create the smooth liquid we pour from a glass. Maybe spacetime bubbles up from an underlying substrate we haven't discovered yet. Understanding that bedrock layer, understanding what spacetime is made of, could reveal entirely new ways to manipulate it. Loop quantum gravity proposes something radical. Spacetime isn't continuous. It's woven, braided from discrete quantum loops and networks, like cosmic fabric stitched together at the Planck scale. If that's true, if spacetime is truly woven rather than poured, then warp drives stop being fantasies. They become engineering challenges we might actually solve. The seams are already there. We just need to learn where to cut. Imagine if reality itself had seams. Imagine if the fabric of spacetime wasn't smooth and seamless, but woven. A tapestry you could unravel and rewove into something entirely different. That's the radical idea at the heart of warp drive physics. Einstein gave us a picture of spacetime as perfectly smooth. But what if he was incomplete? What if spacetime has structure, grain, weakness points where reality itself becomes malleable? If that's true, then somewhere in the universe, there might be cosmic strings. Thin, one-dimensional defects left over from the Big Bang itself. They'd stretch across entire galaxies, carrying the mass density of mountains compressed into a thread thinner than an atom. And if they exist, they might be the universe's way of showing us its own scars, natural demonstrations of how space-time can break and bend. Find one of these cosmic strings, study it, and you might unlock the secret to reshaping reality on demand. But here's the brutal truth. We don't know if any of this is real. Space-time might be exactly as smooth as Einstein said. This entire vision could collapse under scrutiny. But if it doesn't, if space-time is more complex than we imagined, then it might also be more manipulable, and that changes everything. The universe might have already left us hints about how to bend it. We just have to look in the right places. So how close are we actually? The honest answer depends on who you ask. Optimists see working prototypes in 10 to 15 years. Pessimists say centuries. The truth probably lives somewhere between those extremes. But closing that gap means solving one specific, towering obstacle: energy. Warp drives don't just need power. They need amounts of power that make our current civilization look like a candle in a hurricane. And that power must be controlled with precision down to the quantum level. We're making progress on fusion, steady progress, but we haven't achieved sustained net energy yet. Antimatter? We can make it now, but in quantities so microscopic and at costs so astronomical that it's practically useless. Dark energy manipulation exists only on paper. Creating negative energy density at useful scales isn't just hard. It might be impossible with technology that exists, or will exist for centuries. White's team actually detected a nanoscale warp geometry. They measured it. They saw the signature. But scaling that up by a factor of 10 billion? That's not just difficult. That's like going from a single grain of sand to a desert. Except you have to move the entire desert with your bare hands. The Casimir effect, one of our best tools, weakens with distance. Fast. Amplification techniques, those only exist in theoretical papers. Without a breakthrough in quantum vacuum manipulation, a fundamental discovery we haven't made, this problem alone could set us back decades. But energy is just the beginning. Materials science faces demands that border on the impossible. Imagine a spacecraft. Around it, space-time itself is warping violently, contorting just meters away. The structure must stay stable. The hull must hold. Everything inside must survive stresses and radiation that nothing humanity has ever built has endured. We can't test materials against these conditions because we can't create the conditions yet. This is a catch-22, written into physics itself. You need warp fields to build materials that survive warp fields. You need materials that survive to generate the warp fields. Then there's navigation. How do you steer a ship faster than light when you can't see what's in front of you? How do you avoid collisions? What happens if something fails inside a warp bubble traveling at 10 times light speed? Those aren't small engineering problems, they're showstoppers. They demand solutions before any human gets anywhere near this technology. And underneath it all, theoretical physics still has gaps. We can't fully simulate how warp drives actually work. Quantum effects at the bubble's edge remain mysterious. We don't even know if dark energy helps us or creates catastrophic problems we haven't imagined yet. Each unknown is a potential trapdoor. Each uncertainty could hide a fundamental barrier that only reveals itself when we actually try to build this thing. The path to warp drives isn't just long, it's uncertain. Every step forward raises new questions. Every answer births new problems. We might be on the threshold of a revolution, or we might be chasing a beautiful mirage. But we keep pushing forward anyway. Because if even a fraction of this works, if we're wrong about what's impossible, then we might be standing at the edge of the greatest transformation in human history. Picture this. A breakthrough happens. It occurs quietly, in a classified laboratory somewhere on Earth. Maybe in a Pentagon basement. Maybe in a bunker belonging to another nation's military. The discovery that could unlock the stars is immediately stamped secret. The world keeps spinning. The public has no idea. Years pass. Decades even. And when the truth finally emerges, we learn that while civilian scientists were publishing papers and debating theories, military engineers were already building the first warp drive. This is the trap we face. International cooperation would supercharge progress. We could share knowledge, pool resources, accelerate the timeline dramatically. But national security stands in the way. Nations guard breakthroughs, like dragons guard gold. The first warp drive might never be ours to celebrate together. It might be a weapon before it becomes a tool. Here's the brutal math. Right now, warp drive research runs on pocket change. We're talking millions of dollars per year, scattered across programs worldwide. Fusion research gets billions. The Manhattan Project? $27 billion in today's money, compressed into 4 years. Apollo? $150 billion. That was the price we paid for the moon. If we threw that kind of money at warp drives, real, sustained, unwavering commitment, we could have test vehicles in a decade. Without it, progress limps forward, one small step at a time. But here's where it gets interesting. Some researchers, when they let their guard down in private conversations, will tell you something remarkable. A single breakthrough changes everything. One discovery. That's all it takes. Imagine if someone cracked the code on negative energy. Not just theoretically, but actually. Scalable. Usable. Or imagine we finally learned to manipulate dark energy itself. Or stumbled onto some completely unexpected way to bend spacetime that nobody saw coming. The entire timeline collapses. We jump from barely measuring nanoscale effects to building functional prototypes in years, not centuries. History proves this happens repeatedly. Powered flight went from, is it even possible, to routine air travel in just 20 years. Nuclear energy became practical within 5 years of theoretical understanding. Your smartphone is the size of a pocket because computers shrank from room-filling monsters in 30 years. When the right breakthrough happens, progress doesn't creep, it explodes. But, and this is crucial, the universe might not cooperate. Some challenges resist even our most brilliant minds and our deepest pockets. Fusion power has been 30 years away for over 60 years. Quantum computing took decades longer than optimists promised. These barriers hold their ground stubbornly, almost defiantly. So which one is warp drive? Is it a breakthrough waiting to happen, or a cosmic wall we'll spend centuries banging our heads against? The answer depends entirely on whether reality allows it. If the universe permits negative energy generation at the scales we need, if dark energy can be manipulated like we manipulate electricity, if stable warp fields can actually exist without tearing space-time apart, if these things are possible, truly possible, then it becomes a race, an engineering problem. Difficult, yes, but solvable. If the universe says no, if there are protections built into the very laws of physics that prevent these effects from working at useful scales, then we might pursue warp drives forever and come up empty. There's only one way to find out. Keep pushing. Fund the research. Build better instruments. Run more experiments. Test ideas that sound wild. Someone, somewhere, needs to find the key. And when they do, when that lock finally clicks open, the countdown begins. But why does this matter? Why should you care about warp drives at all? Because faster-than-light travel is more than just a technical achievement. It's a fundamental transformation of what humanity can become. Every great migration in our history, out of Africa, across oceans to new continents, expanded our potential. It forced us to adapt, to innovate, to dream bigger. The stars are our next frontier, and we can only reach them if we can get there. With warp drives, the galaxy stops being an abstract concept in a telescope. It becomes accessible. Hundreds of potentially habitable planets within 50 light years suddenly become destinations. Real places. Real homes. We could establish colonies on worlds far more suited to life than Mars will ever be. Humanity would spread across multiple star systems. We would stop being a single planet species, balanced on a knife's edge of existential risk. We would become a multi-world civilization with redundancy, with resilience, with a future that can't be erased by a single asteroid, or plague, or war. And that's just the survival angle. The economic implications are staggering. Asteroid mining becomes trivial when you can warp to the asteroid belt and back in ours. Rare elements abundant in other solar systems could be harvested and returned. Energy resources from stars and gas giants make Earth's entire current economy look like pocket change. A spacefaring civilization with warp capability would command resources beyond anything we can currently imagine. But maybe the real value isn't measured in dollars. Maybe it's measured in possibility, in wonder, in the realization that the universe, for all its vastness and indifference, might actually let us reach for it. All we have to do is keep looking, keep pushing, and maybe, just maybe, we'll find the key. Picture this. We're standing at the edge of everything we know. The stars stretch out above us, billions of them, each one potentially hosting worlds we've never seen, life we've never met, mysteries we've never solved. But right now, they might as well be unreachable. Everything changes if we crack the code of warp drive physics. Suddenly, those distant worlds aren't theoretical anymore. They're destinations. We could stop squinting at exoplanets through telescopes and actually visit them. We could land on alien worlds and study their ecosystems directly, not through guesswork, but through hands-on investigation. We could watch stars being born, observe black holes up close, study neutron stars with instruments we place on their surfaces. The biggest questions humanity has ever asked. Where did life come from? How do planets form? What is the universe really made of? Stop being philosophical debates and become answerable through direct observation. Every world we visit rewrites the textbooks. Every discovery challenges what we thought we knew. But here's where it gets truly extraordinary: the possibility of contact. If intelligent civilizations exist anywhere within reach, we don't have to wait centuries for their radio signals to crawl across the void. We could go there. We could search for them. We might find the ruins of dead civilizations, or encounter life just beginning to emerge from the oceans, or come face to face with intelligence that rivals our own, or dwarfs it entirely. The philosophical implications are staggering. Religion, philosophy, human identity itself. Everything we believe about our place in the cosmos would be fundamentally rewritten. And that's just the beginning. A humanity scattered across the stars wouldn't stay unified. Isolated colonies would develop their own languages, their own customs, their own cultures, shaped by alien worlds we can barely imagine. We might split into distinct branches of human civilization, fundamentally different versions of ourselves, adapted to different worlds, or we might stay connected through warp-capable vessels, maintaining a galactic civilization unlike anything in history. Either way, the future stops looking like anything recognizable today. But let's be honest about what else becomes possible. The same technology that lets us explore the cosmos becomes a weapon beyond anything we've built before. A nation or group that masters warp drive technology would dominate every other power on Earth. Warfare could explode across space on scales that make our worst conflicts look like bar fights. And history tells us something sobering. We're terrible at preventing militarization. We keep trying, and we keep failing. Then there are the questions nobody's asking yet, but should be. What happens to spacetime itself when we repeatedly tear warp bubbles through it? Does it damage reality? Could we accidentally destabilize regions of space through overuse? Could warp travel leave behind some kind of cosmic pollution? Consequences that accumulate year after year until we've poisoned the universe? We don't know, and we need answers. Before we start doing it routinely, the ethical minefields are just as treacherous. Who gets access to warp ships? How do we prevent the exploitation of newly discovered worlds? If we find primitive life, organisms just learning to survive, do we have a moral obligation to leave them alone? What rights do people born on distant colonies have to independence from Earth? These aren't abstract philosophy problems. These are conflicts that could define the future of human civilization. But perhaps the most profound change would be psychological. Right now, we are prisoners on a fragile world, orbiting an ordinary star in an ordinary galaxy. Space is something we watch. It's something we study from a distance. But knowing, truly knowing, that we can reach the stars, that we can walk on other worlds, that the cosmos is open to us, that fundamentally changes how humans think about themselves. We stop being confined and become free. The possibility space for human achievement, for human experience, expands beyond measure. The Apollo program inspired millions of people across generations, and it barely scratched the lunar surface. Imagine what a warp drive would do. Imagine knowing that your children's children could build civilizations on worlds orbiting different stars. This moment, right now, as physicists in laboratories around the world inch closer to understanding whether warp drive physics is actually possible, might be the hinge upon which the entire future of humanity swings. Either we solve this, we crack it, we become a civilization of the stars, spreading across the galaxy, learning from 1,000 worlds, encountering intelligence we never knew existed. We transcend the cosmic prison, or we don't. We remain confined to our little corner of space, trapped forever. But here's the catch. The choice might not actually be ours. The universe decides whether the physics allows what we need. Reality might simply forbid it. No matter how clever we are, no matter how hard we try, the laws of nature might say no. Or, and this is just as possible, those same laws might have already handed us everything we need. We just haven't figured out the combination yet. Either way, the attempt itself matters. Every researcher running quantum simulations, measuring nanoscale distortions, testing the boundaries of what's theoretically possible, they're not just chasing an impossible dream. They're expanding the frontiers of human knowledge. The technologies we develop pursuing this goal will spin off applications benefiting humanity for generations, even if warp drives never materialize. We learn by trying to do things that seem impossible. And sometimes, just sometimes, we succeed. The scientists working in labs today are trailblazers. They might not see the payoff for decades, but they're exploring the edge of physics. And that exploration itself is how we learn what's really possible. Someone, somewhere, is working on a problem they may never see solved. They're chasing an answer that won't benefit them, maybe won't benefit their children or their grandchildren either. But they work anyway. This is the thinking that built everything. Every cathedral, every bridge, every cure, every technology that changed what it means to be human. And right now, someone reading this could be that person. Maybe you're the engineer who finally cracks the negative energy generator, the physicist who unlocks the secrets of dark energy itself, the programmer who writes the code that makes warp fields real, not theoretical, but tangible, controllable, real time. The breakthrough could come from anywhere, from anyone willing to look at an impossible problem and refuse to accept the answer, never. Here's what we're up against. The universe is incomprehensibly vast. Light from the farthest edge we can see has been traveling toward us for over 13 billion years, and it will never arrive, because space itself is expanding faster than light can cross it. We exist in a tiny bubble, a prison of causality. We can only interact with the region of space where light has had time to reach us since the Big Bang itself. Warp drives won't change that fundamental cosmic limit. But here's the thing, they don't need to. Even at 1,000 times the speed of light, 1,000 times faster than our fastest radio signals can travel, crossing the observable universe would still take millions of years. Impossible. Unreachable. But warp drives would do something far more profound. They would transform what's practically achievable. They would compress cosmic distances into human timescales. The Andromeda Galaxy, billions of worlds, countless unknowns. Right now, it's utterly unreachable. But at 10 times light speed, it becomes accessible. Within a human lifetime. Within reach. That's the real prize. Not godlike power. Not infinite reach across the cosmos. Just the simple, profound ability to explore our cosmic neighborhood. To visit nearby stars. To investigate the promising worlds our telescopes already show us. To finally establish humanity beyond Earth. While Earth remains our home. This isn't about national prestige or scientific curiosity alone. This is about the future of our species. It's the difference between humanity becoming a multi-world civilization or remaining forever confined to a single planet. Watching the cosmos through telescopes, forever on the outside looking in. And that future is being written right now. In laboratories, in equations scribbled on whiteboards, in experiments that push the boundaries of what we thought was possible. One breakthrough at a time. The next chapter of human history isn't written yet, but it's being written. And it might arrive sooner than any of us expect.